Hello there and welcome to Life Beyond Seen, where curiosity settles in comfortably, complex science slows to an easy pace, and the natural world gets explored in a way that feels calm rather than overwhelming. Tonight's quiet exploration moves into landscapes that many people find fascinating, sometimes beautiful, occasionally unsettling, and often misunderstood. We're talking about swamps, those waterlogged stretches of land where solid ground, open water, plants, animals and climate all mix into something that does not always behave the way we expect. Swamps have a reputation. Some people picture mist hovering over dark water, others imagine thick vegetation, insects humming constantly, and the sense that stepping off a safe path might lead somewhere difficult to return from. Yet at the same time, these places support huge biodiversity, regulate climate, store carbon, and quietly keep ecosystems functioning. They are not simply dangerous wastelands, they are living systems. Still, they can also be among the most challenging environments on Earth for humans to navigate safely, and understanding why turns out to be surprisingly interesting. Before we go further, a small moment of curiosity feels fitting. Where are you listening from tonight, and what time is it there right now? It is always interesting to think about people scattered across different places, some hearing this before sleep, others during a commute, maybe someone listening while rain taps a window or while evening settles outside. Different settings, same conversation, all happening at once. And if you find this kind of slow, thoughtful journey into science relaxing or engaging, feel free to leave a like, maybe subscribe. Perhaps share it with someone who enjoys learning in a calm way. It helps this little corner reach more people who appreciate quiet exploration without urgency or noise. Now settling gently into the topic itself, it helps to start with something simple. A swamp is not just any wet place. It is a specific kind of wetland ecosystem where water saturates the ground for long periods, often year-round, and where trees or tall vegetation grow directly out of that soaked soil. Unlike marshes, which are dominated mostly by grasses, swamps usually have woody plants, shrubs, or full forests adapted to standing water. The key detail is persistence. Water is not passing through quickly. It lingers, it accumulates, it changes the soil, the air, the chemistry, and the types of life that can survive there. That constant presence of water reshapes everything. Soil becomes soft, sometimes unstable. Oxygen levels drop underground because water blocks airflow. Decay slows in unusual ways, creating thick organic layers like peat. Microorganisms flourish, insects multiply, plants evolve specialized routes to cope with low oxygen, animals adapt to hunting or hiding in dense vegetation. It becomes an ecosystem built around saturation. From a distance, many swamps look peaceful. Calm water reflects trees. Bird calls echo. Sunlight filters through leaves. The surface often appears still. Yet that calm appearance can hide very real challenges. The ground beneath shallow water may not support weight. Hidden channels or sinkholes may exist. Some plants irritate skin or release toxins. Insects carry diseases. Predators find ideal cover. Heat and humidity combine to exhaust visitors faster than they expect. Navigation becomes tricky because landmarks repeat, and visibility stays limited. It is not that swamps are hostile by intention. They simply function according to ecological rules that humans did not evolve to handle easily. When people move through them without preparation, the environment does not adjust. The environment just continues being a swamp. Historically, that mismatch shaped how societies viewed wetlands. Many ancient settlements avoided them unless resources demanded otherwise. Travel accounts from explorers frequently describe swamps as obstacles rather than destinations. Early infrastructure projects often aimed to drain wetlands for agriculture or urban expansion. Only later did science begin to show how vital these ecosystems actually are for flood control, carbon storage and biodiversity protection. That shift in understanding has been gradual, Even today, swamps still carry a mixed reputation. Conservationists emphasize their ecological importance, while outdoor survival experts emphasize caution. Both perspectives can be true at the same time. Appreciating their role does not remove the practical risks they pose. One immediate challenge people notice in swamps is footing. Solid ground becomes unpredictable. Soil saturated with water loses structural strength. What appears firm may suddenly give way. Peat layers can behave almost like sponges. A step that feels stable one moment may sink slowly the next. It is rarely dramatic quicksand like films portray, but gradual sinking combined with heavy vegetation can trap someone long enough to cause serious problems, especially if fatigue or dehydration sets in. Water depth itself can also be deceptive. Swamps often contain shallow pools interrupted by deeper channels carved by slow currents or animal movement. Murky water hides these variations. Without clear visibility, stepping forward becomes guesswork. A sudden drop into deeper water can happen, even when the surrounding area looks uniformly shallow. And then there is the air. Swamps frequently sit in warm, humid climates where evaporation stays high, but airflow remains low because vegetation blocks wind. Humidity reduces the body's ability to cool through sweating. Heat exhaustion can develop quickly, sometimes before a person realizes how much energy they are expending. Add insects, uneven terrain, and the need for constant alertness, and fatigue builds steadily. Mosquitoes are often the first wildlife people associate with swamps, and that association is not exaggerated. Standing water creates ideal breeding conditions. In some regions, mosquito populations become dense enough to influence daily human activity. Historically, diseases like malaria, dengue, and West Nile virus have been linked strongly to wetland environments. Modern medicine and prevention methods help significantly, but the ecological connection remains. Other insects join that environment too. Biting flies, ticks, and various aquatic larvae all thrive in moist habitats. Some carry pathogens, others simply create constant irritation that drains attention and energy. Over time, even small discomforts accumulate, making navigation harder and decision-making less reliable. Vegetation adds another layer of complexity. Swamp plants often develop defenses against herbivores and competition. Some produce irritating sap, others have thorns or sharp edges. Certain species release toxins that cause skin reactions. Thick undergrowth reduces visibility and limits movement. Branches, vines, and roots create obstacles at every level, from ankle height to overhead. Interestingly, many animals find exactly those conditions advantageous. Dense vegetation provides camouflage. Water muffles sound. Limited visibility allows ambush predators to approach prey undetected. Reptiles, amphibians, birds, and mammals all exploit that structure. For humans unfamiliar with reading subtle environmental cues, detecting wildlife presence becomes harder. Humidity also affects equipment. Clothing stays damp. Electronics struggle without protection. Food storage becomes complicated because moisture encourages spoilage. Fire starting becomes difficult, reducing access to warmth or cooking. These are small logistical issues individually, but together they shape survival outcomes. Navigation deserves careful attention too. In forests or mountains, landmarks often stand out clearly. In swamps, repetition dominates. Similar trees, similar water channels, similar plant clusters appear in every direction. Magnetic compasses can be affected locally by mineral deposits. GPS signals may weaken under dense canopy. Without strong orientation skills, people can circle back unknowingly. Historical records include many accounts of travellers becoming disoriented in wetlands, despite short intended journeys. Search and rescue teams still treat swamp environments cautiously for exactly this reason. The terrain slows movement, complicates communication, and introduces health risks for rescuers as well as those being assisted. Even sound behaves differently. Dense vegetation absorbs some frequencies while water reflects others. Distances become hard to judge. Animal calls may seem closer or farther than they are. Human voices may not carry as expected. This subtle acoustic distortion can increase feelings of isolation. Psychologically, that isolation matters. Environments with limited visibility, constant insect noise, humidity, and uncertain footing place continuous cognitive load on visitors. Attention stays elevated. Fatigue increases faster. Decision errors become more likely. People sometimes underestimate how much mental energy unfamiliar terrain consumes. Despite all this, swamps are far from lifeless danger zones. They are among the most productive ecosystems globally. Fish breed there, birds nest there, amphibians depend on those water conditions. Plants filter pollutants, carbon accumulates in waterlogged soils rather than releasing quickly into the atmosphere. Floodwaters spread out safely instead of rushing downstream destructively. Understanding both sides at once helps explain why swamps attract scientific study, conservation efforts, and careful ecotourism. Researchers monitor climate effects there. Biologists document species interactions. Hydrologists study water cycles. Each visit requires preparation, respect for conditions, and awareness that the ecosystem will not accommodate human expectations automatically. Another aspect that often surprises people is how quickly weather can alter swamp conditions. Heavy rainfall raises water levels rapidly because drainage remains slow. Paths disappear. Previously stable ground softens further. Animal movement patterns shift. Visibility drops. Temperature changes influence insect activity. Conditions that seemed manageable in the morning may feel very different by afternoon. Light itself plays a role. Tree cover reduces direct sunlight, creating dim environments even during daytime. That reduced light complicates navigation and affects depth perception. Reflections on water surfaces further distort visual cues. Sunglasses, often helpful elsewhere, may hinder rather than help under dense canopy. Clothing choices become practical science in these environments. Breathable fabrics reduce heat stress but must also protect against insects and vegetation. Waterproof boots help until water overtops them. Quick-dry materials prevent prolonged dampness. These details sound small, yet they strongly influence comfort, safety, and endurance. Hydration requires attention too. Abundant water does not equal safe drinking water. Swamps often contain microorganisms, parasites, or chemical compounds unsuitable for direct consumption. Filtration, purification tablets, or boiling become essential. Without preparation, dehydration risk increases despite being surrounded by water. And while all of these factors combine physically, they also shape perception. Popular media often exaggerate swamp danger dramatically, yet the underlying risks are real enough without exaggeration. Films show dramatic sinking, constant predator attacks, or supernatural elements. Reality usually involves subtler challenges: exhaustion, disorientation, infection risk, environmental exposure. Less cinematic, but no less significant. As conversations about ecosystems continue, swamps provide an interesting example of how beauty, ecological importance, and practical hazard coexist. Recognizing that balance allows for appreciation without complacency. It encourages curiosity paired with preparation rather than avoidance or romanticization. Looking closer at how soil forms under constant saturation begins to explain why footing remains unpredictable, why certain gases accumulate near the surface, and why some areas support trees while others remain open water, all of which ties directly into how these environments function day to day, and why simply walking through one can feel straightforward at first, yet steadily more complicated the deeper you go. When people hear the word swamp, they often picture a vague mix of shallow water, trees, insects, and mud. But in ecology, the term has a specific meaning. A swamp is a type of wetland ecosystem, where the ground stays saturated or flooded for long periods, and where woody plants, usually trees or shrubs, dominate the vegetation. That combination of persistent water and woody plant growth distinguishes swamps from other wetlands like marshes, bogs and fens. Each wetland type has its own water chemistry, soil formation process, plant community and ecological role, and mixing them together can make it harder to understand why some of them present greater physical challenges to humans than others. The most important feature of a swamp is hydrology, meaning how water enters, moves through and leaves the system. Swamps receive water from several sources. Rainfall contributes directly, especially in tropical and subtropical regions where heavy precipitation keeps soil saturated for months. Rivers may overflow seasonally, depositing water and sediment into adjacent lowlands that become forested wetlands. Groundwater can seep upward through soil layers, maintaining constant moisture even during dry periods. Coastal swamps also experience tidal flooding, introducing salt water periodically. Each source affects the chemistry, vegetation and animal life present. Water persistence changes soil characteristics dramatically. In well-drained soils, oxygen circulates freely, allowing microbes to break down organic material quickly. In a swamp, water fills air spaces in the soil, limiting oxygen availability. Decomposition slows, and partially decayed plant material accumulates. Over time, this creates thick organic layers, often dark, soft, and rich in carbon. Peat formation in some swamp systems illustrates this process clearly. Peat soils compress easily under weight, which explains why firm-looking ground can suddenly feel unstable. Tree species growing in swamps have adaptations that allow survival under low-oxygen soil conditions. Some develop buttressed trunks for structural support in soft ground. Others produce aerial roots or pneumatophores, which extend above the water surface to absorb oxygen directly from the air. Cypress trees in North American swamps show this clearly with their knees, woody projections that rise from submerged roots. Mangrove species in coastal swamps form intricate root networks that stabilize sediment while allowing gas exchange. These structural adaptations also create complex terrain that complicates walking routes for humans. Water chemistry varies widely among swamps. Freshwater swamps receive limited dissolved salts and usually support diverse fish, amphibians, birds, and mammals. Saltwater swamps, including mangrove forests, tolerate tidal influx and host species adapted to brackish or saline conditions. There are also intermediate systems with fluctuating salinity depending on seasonal weather. Chemical composition influences everything from plant distribution to disease ecology, because certain microorganisms thrive better under specific conditions. Temperature interacts strongly with swamp ecology. Warm climates accelerate biological activity, increasing plant growth and microbial populations. That leads to higher insect densities, faster organic matter accumulation, and greater biodiversity overall. Cold climate swamps exist as well, particularly in boreal regions, but biological activity proceeds more slowly there. Ice cover in winter changes water flow, oxygen availability, and animal behaviour. Even so, saturated soils remain characteristic. Light availability also shapes swamp ecosystems. Dense tree canopies reduce sunlight reaching the ground. Understory plants adapt to lower light conditions. Algae growth in open water areas varies accordingly. Reduced light contributes to cooler ground temperatures in some seasons, but also limits evaporation, which helps maintain soil moisture. From a practical perspective, reduced light levels can make navigation harder because visual contrast decreases and depth perception becomes less reliable. Animal communities in swamps reflect the constant presence of water and dense vegetation. Amphibians often thrive because breeding sites remain available year-round. Reptiles use water for thermoregulation and hunting. Birds exploit nesting sites protected by water barriers that deter terrestrial predators. Mammals adapted to semi-aquatic life, such as otters or swamp deer, move efficiently through terrain that slows other species. Insects, especially mosquitoes, find ideal breeding conditions in standing water with abundant organic material. These biological factors tie directly into the perception of swamps as dangerous ecosystems. High biodiversity includes species capable of defending territory, transmitting disease, or exploiting camouflage effectively. Still, danger usually arises from environmental conditions rather than deliberate aggression by wildlife. Animals typically avoid humans when possible. The difficulty lies in recognizing their presence before close proximity occurs. Water movement in swamps is generally slow compared with rivers or streams. That slow flow allows sediment to settle and organic matter to accumulate. Over time, channels shift gradually rather than dramatically. Seasonal flooding may expand water coverage temporarily, creating new pools and altering established pathways. Because changes can be subtle, maps quickly become outdated unless updated frequently. Human interaction with swamps has a long history. Agricultural societies often drained wetlands to create farmland. Urban expansion replaced many swamps with infrastructure. These modifications sometimes led to unintended consequences, including increased flood risk, reduced biodiversity, and changes in local climate regulation. Modern conservation efforts increasingly emphasize preserving or restoring wetlands because of their ecological services, including water filtration and carbon storage. Terminology differences matter when discussing wetlands scientifically. Marshes typically feature grasses and herbaceous plants rather than trees. Bogs receive most water from rainfall and often have acidic conditions with specialized vegetation like sphagnum moss. Fens receive mineral-rich groundwater and support different plant communities. Swamps specifically involve woody vegetation and persistent saturation. Understanding that distinction clarifies why certain hazards, such as unstable root systems or dense canopy cover, occur more often in swamps. Hydrological cycles connect swamps to larger environmental systems. During heavy rainfall, swamps act as natural sponges, absorbing excess water and releasing it slowly. That reduces downstream flooding. Vegetation traps sediment, improving water clarity elsewhere. Nutrient cycling within swamps supports fisheries and agricultural productivity indirectly. These functions illustrate why eliminating swamps entirely can create environmental imbalances. Gas exchange in swamp soils presents another interesting aspect. Anaerobic decomposition produces methane and other gases. In poorly ventilated conditions, these gases may accumulate near the ground surface. Usually concentrations remain low outdoors, but localized pockets can affect plant growth or contribute to odor. Methane emissions from wetlands also factor into climate research, as wetlands represent both carbon sinks and methane sources depending on conditions. Seasonal variability influences swamp characteristics significantly. Dry seasons may lower water levels, exposing mudflats temporarily. Wet seasons expand flooded areas. Plant growth cycles respond accordingly. Animal migration patterns follow water availability. For someone unfamiliar with local seasonal rhythms, timing a visit incorrectly can increase difficulty dramatically. Terrain that appears accessible one month may become impassable the next. Swamps also influence regional weather patterns. Large wetland areas moderate temperature fluctuations by storing heat during the day and releasing it slowly at night. Evapotranspiration from vegetation contributes moisture to the atmosphere, affecting humidity and sometimes precipitation patterns nearby. These interactions highlight the broader climatic role wetlands play. Microbial communities in swamps perform essential ecological functions. Bacteria and fungi break down organic material, recycle nutrients, and influence soil chemistry. Some microorganisms fix nitrogen, making it available for plant growth. Others participate in sulfur cycling. While invisible to casual observers, microbial processes shape the entire ecosystem structure. Water clarity varies widely. Some swamps contain tannin-rich water from decomposing plant material, giving it a dark colour similar to tea. Reduced visibility complicates underwater observation and increases uncertainty about depth or obstacles. Clearer swamp waters exist too, especially where groundwater inflow dominates, but turbidity often increases after storms or seasonal flooding. Human health considerations arise mainly from pathogens associated with standing water. Mosquito-borne diseases historically shape settlement patterns near wetlands. Modern public health measures reduce risks significantly, yet awareness remains important. Protective clothing, repellents, and vaccination programs in certain regions reflect that ongoing relationship between wetlands and disease ecology. Swamps also present economic resources. Timber harvesting from swamp-adapted trees, fisheries supported by wetland nurseries, and ecotourism all depend on these ecosystems. Sustainable management practices aim to balance economic use with conservation. Overexploitation can degrade wetland function, increasing environmental risks elsewhere. Transportation through swamps historically relied on waterways. Canoes, small boats, and raised walkways allowed movement where roads proved impractical. Modern infrastructure sometimes incorporates elevated boardwalks for both access and ecosystem protection. These solutions reduce ground disturbance while providing safe passage. Acoustic environments in swamps differ from open landscapes. Dense vegetation dampens some sounds while water surfaces reflect others. Animal calls carry unpredictably. That acoustic complexity affects wildlife communication and human perception alike. It also contributes to the sensory experience many people associate with wetlands. Fire behaviour in swamps contrasts with dry forests. Saturated soils usually inhibit surface fires, but accumulated peat can burn slowly underground during drought conditions. Such peat fires produce long-lasting smoke and are difficult to extinguish. This factor has implications for land management and climate considerations. Cultural associations with swamps vary globally. Some communities view them as valuable resources integral to traditional livelihoods. Others historically regarded them as unhealthy or inhospitable. Literature and media often emphasize mystery or danger. Scientific understanding provides a more balanced perspective, recognizing both ecological importance and practical challenges. Technological advances continue improving swamp study methods. Remote sensing, satellite imagery, and environmental DNA sampling help researchers monitor biodiversity and hydrology without constant physical presence. These tools expand knowledge while minimizing disturbance. Educational outreach about wetlands has grown in recent decades. Schools, conservation groups, and public agencies emphasize wetland preservation. Awareness campaigns highlight flood control, biodiversity support, and climate regulation roles. Increasing public familiarity may gradually shift perception from avoidance toward informed respect. As understanding of swamp ecosystems deepens, connections between physical structure, biological communities, and human interaction become clearer. Persistent water shapes soil. Soil influences vegetation. Vegetation structures habitat. Habitat determines wildlife presence. All of these elements together influence how people experience these landscapes when they enter them, and that interconnected system leads naturally into a closer look at how appearances can mislead visitors who expect something simpler than what actually exists on the ground. At first glance, a swamp can look surprisingly peaceful. Calm water often reflects the sky like glass. Trees rise straight out of the surface, sometimes draped in moss, sometimes surrounded by still pools where ripples move slowly and quietly. Birds call intermittently. Insects hum in a steady background rhythm. Sunlight filters through branches in scattered beams. For someone approaching the edge of a wetland without much prior experience, the initial impression is often tranquility rather than danger. Nothing appears rushed. Nothing obviously threatening stands out immediately. The landscape feels quiet, almost suspended. That initial perception has influenced how swamps appear in photography, travel writing, and nature documentaries. Images emphasize reflective water, striking plant shapes, unusual wildlife, and the sense of isolation. These visuals are accurate in a limited sense, but they do not always convey how physically demanding or unpredictable the environment can be once someone actually enters it. The difference between observing a swamp and moving through one becomes clear very quickly. Part of that contrast comes from visibility. From a distance, water surfaces appear smooth and continuous. Depth is hard to judge because colour, reflections, and vegetation obscure the bottom. What looks like shallow water may hide deeper channels, submerged logs, or soft sediment. Without stepping in, the viewer has no reliable way to assess stability. This visual ambiguity contributes strongly to the mismatch between first impressions and practical reality. Ground conditions reinforce that effect. Soil in swamps rarely behaves like dry earth. Saturated organic material compresses under weight. Roots, decomposing plant matter, and water pockets create uneven support. Even experienced field researchers move cautiously, because what looks solid may not remain so after repeated steps. The slow sinking sensation can feel subtle at first, but it increases physical effort and sometimes creates situations where extraction becomes difficult without assistance. Vegetation adds another layer. Dense plant growth limits sight lines. Trees, shrubs, reeds, and vines often grow close together because constant water availability supports continuous growth. From outside the swamp, this density reads as lush greenery. Inside, it becomes an obstacle course. Branches restrict movement. Roots protrude unpredictably. Vines catch on clothing and equipment. Navigation requires attention to every step, which quickly reduces travel speed and increases fatigue. Humidity plays a major role in how environments feel once entered. Warm swamp air often carries high moisture content because evaporation from standing water combines with plant transpiration. That moisture interferes with the body's cooling mechanisms. Sweat evaporates less efficiently, leading to heat accumulation even during moderate physical activity. Someone who initially found the environment calm may begin feeling overheated faster than expected. Insects frequently intensify that experience. From a distance, insect presence might register only as faint sound. Up close, density becomes clear. Mosquitoes, flies, midges, and other insects thrive in standing water habitats. Protective clothing and repellents help, but sustained exposure still demands attention. Swatting, adjusting clothing, and monitoring bites consume mental energy that might otherwise go toward navigation or observation. Sound perception also shifts once inside a swamp. Open landscapes allow sound to travel predictably. Dense vegetation absorbs certain frequencies, while water reflects others. Animal calls may seem closer or farther than they are. Human voices may not carry far. That acoustic unpredictability can make orientation harder and contribute subtly to disorientation. Temperature stability sometimes adds to the misleading calm. Swamps often experience less dramatic daily temperature fluctuation because water stores heat. That moderation can feel pleasant initially. However, combined with humidity, it maintains a consistently warm environment that prevents the body from cooling during rest periods. Over time, this contributes to cumulative heat stress. Water clarity further complicates perception. Some swamps contain tannin-stained water that appears dark brown or black. Reflections become strong. Bottom features remain invisible even in shallow areas. Other swamps contain suspended sediment that clouds visibility. Without visual cues, stepping decisions rely on probing or prior knowledge, rather than simple observation. Wildlife visibility operates similarly. Many swamp animals rely on camouflage. Reptiles, amphibians, birds and mammals often blend into vegetation or water surfaces effectively. Their presence may go unnoticed until very close proximity. Most animals avoid confrontation, but surprise encounters can startle both humans and wildlife, increasing risk for defensive reactions. Light filtering through canopy cover affects perception continuously. Bright overhead sunlight becomes diffused. Contrast decreases. Depth cues weaken. Navigating uneven terrain under those lighting conditions requires extra caution. Eye strain can increase as individuals try to distinguish safe footing from hazards. Another factor shaping first impressions is smell. Wetlands often carry distinctive scents from decomposing plant material, microbial activity, and stagnant water. Initially, these smells may seem earthy or organic. Over time, stronger odours can indicate anaerobic decomposition or gas release. While usually not dangerous outdoors, persistent odours contribute to sensory fatigue. Psychological response plays a significant role in how environments feel. Humans evolved largely in environments where ground stability and visibility were higher. Entering a swamp challenges those expectations. The need for constant vigilance elevates stress subtly. Even when no immediate threat exists, the environment requires sustained attention, which people often interpret as discomfort or unease. Cultural narratives reinforce that psychological effect. Literature, films, and folklore frequently portray swamps as mysterious or threatening. While dramatized, those portrayals influence expectations. Visitors may arrive either overly cautious or dismissive depending on prior exposure. Balanced understanding tends to produce safer outcomes. Historical exploration accounts often mention this contrast explicitly. Early travellers described swamps as deceptively calm landscapes that became exhausting and hazardous upon entry. Accounts from tropical expeditions frequently note slower progress than anticipated, unexpected illness due to insects or water exposure, and navigation difficulties despite seemingly straightforward terrain. Modern outdoor recreation reflects similar patterns. Hikers accustomed to forest trails sometimes underestimate swamp terrain. Birdwatchers seeking wetland species learn quickly that specialised footwear and planning matter. Researchers working regularly in wetlands develop movement techniques, equipment strategies, and risk assessment habits that differ from those used elsewhere. Water movement itself contributes to subtle risk. Although swamps generally have slow currents, seasonal flooding or hidden channels may introduce localised flow. These currents rarely resemble rivers, but can still destabilise footing. Combined with soft sediment, they increase effort required to maintain balance. Plant chemistry occasionally surprises visitors too. Some swamp plants contain irritants or toxins as defence mechanisms. Contact with certain species can cause skin irritation, rashes, or allergic reactions. Awareness of local vegetation helps reduce exposure, but identification requires experience. Visibility changes rapidly with weather conditions. Fog forms easily over warm water during cool mornings or evenings. Rain reduces contrast further and increases water levels. Wind may bend vegetation, altering familiar landmarks. All these changes affect orientation and movement safety. Equipment performance differs in wet environments. Electronics require waterproofing. Clothing choices influence comfort significantly. Food storage needs protection from moisture. Navigation tools must function reliably under canopy cover. Planning for these factors reduces risk, but requires prior knowledge. Transportation through swamps historically relied on watercraft rather than foot travel. Canoes, small boats, and elevated walkways provide more predictable movement than walking directly on saturated soil. This historical adaptation highlights how environmental conditions shape human solutions. Ecological productivity partly explains why swamps look inviting. Abundant plant growth, bird activity, and water surfaces create visually rich landscapes. Those features attract photographers, naturalists, and tourists. Infrastructure like boardwalks allows safe observation while protecting fragile ecosystems. Flood mitigation benefits provided by swamps often remain invisible during casual visits. These ecosystems absorb excess rainfall and release it gradually. Without them, downstream flooding increases. This protective role contributes to their conservation importance despite local movement challenges. Carbon storage in swamp soils also draws scientific attention. Waterlogged conditions slow decomposition, allowing organic carbon accumulation. Disturbing these soils through drainage or development releases stored carbon into the atmosphere, influencing climate dynamics. Recognizing this function encourages preservation. Scientific fieldwork in swamps requires planning beyond standard outdoor preparation. Researchers monitor hydration, insect exposure, weather forecasts, and emergency access routes carefully. Teams often work in pairs or groups to enhance safety. Communication protocols account for limited signal coverage. Education programs introducing wetlands emphasize observation before entry. Learning to read vegetation patterns, watercolor, animal signs, and seasonal indicators helps visitors interpret environments accurately. That knowledge narrows the gap between first impression and operational reality. Perception gradually shifts with familiarity. Individuals who spend time studying wetlands begin noticing subtler cues, slight elevation changes indicating firmer ground, plant species suggesting water depth, bird behavior hinting at nearby predators. Experience transforms uncertainty into informed caution. Even so, unpredictability never disappears entirely. Wetlands remain dynamic systems influenced by rainfall, temperature, biological activity, and human impact. Respect for that variability underpins safe interaction. Understanding how beauty and risk coexist in swamps prepares the ground for examining more specific environmental factors that influence safety, starting with the physical structure underfoot, because what looks like simple mud or shallow water often turns out to involve complex soil composition, root networks, and hidden channels that shape every step taken deeper into these ecosystems. If someone approaches a swamp expecting something like soft forest soil or a shallow puddle stretched over flat ground, the first few steps usually correct that assumption quickly. Wetland ground behaves differently because it forms under constant saturation. Water changes how soil particles bind together, how organic matter accumulates, and how pressure distributes under weight. The result is terrain that can appear solid while actually resting on layers that compress, shift, or even move slowly beneath the surface. Understanding this structure helps explain why footing becomes one of the most immediate challenges in swamp environments. Most swamp soil contains a high proportion of organic material. Leaves, branches, roots, algae, and other biological debris fall into the water and decompose slowly because oxygen levels stay low. Instead of breaking down completely, they accumulate into dark, fibrous layers. Over time, this material forms peat, a dense organic substrate that stores water efficiently. Peat can support plant growth and even large trees, yet its internal structure remains spongy. Pressure applied from above compresses it gradually, often unevenly. That compression creates the familiar sinking sensation people notice when walking through wetlands. The surface might hold initially, but weight redistributes water within the peat layer, causing gradual descent. Unlike dramatic cinematic quicksand scenarios, most peat compression happens slowly. The danger lies less in sudden engulfment and more in fatigue, instability, and the potential for becoming stuck if footwear or equipment becomes embedded deeply enough. Mud layers complicate the picture further. Swamp mud often consists of fine mineral particles mixed with organic matter and water. Because water occupies the spaces between particles, friction decreases. When weight presses down, the mixture flows slightly rather than resisting firmly. Removing a foot from such mud sometimes requires noticeable effort, because suction develops as water tries to fill the space left behind. That repeated resistance increases energy expenditure significantly during long traverses. Water distribution underground adds another variable. Swamps rarely have uniform saturation. Small channels carry slow-moving water beneath vegetation. Animal paths carve shallow trenches. Seasonal flooding reshapes sediment deposition. These hidden water pathways mean that two steps taken close together may encounter very different support conditions. One area might feel stable, while another yields immediately. Root systems influence stability too. Trees growing in wetlands adapt to low oxygen soils by spreading roots laterally near the surface or developing aerial structures. These roots can create temporary platforms, but they are irregular and sometimes slippery. Stepping on them without noticing can lead to sudden imbalance. In dense swamp forests, root networks overlap extensively, creating uneven terrain concealed beneath leaves or shallow water. Surface vegetation sometimes masks underlying conditions. Floating plant mats form where grasses, mosses and algae intertwine over water or soft peat. From above, these mats may resemble solid ground. In reality, they behave more like flexible rafts. Weight distribution determines whether they support a person briefly or collapse partially into the water below. Experienced wetland researchers test such surfaces cautiously before committing full weight. Water depth variability presents another challenge. Swamps often include shallow pools interspersed with deeper pockets. Sediment colour, plant type and water clarity provide clues, but interpreting them requires familiarity. Murky water hides depth effectively. A step expecting ankle depth may encounter knee or waist depth unexpectedly, increasing risk of falls or equipment damage. Hidden logs and debris contribute to uneven footing. Fallen trees decompose slowly in saturated environments. Branches may lie just below the surface. Contact with such obstacles can destabilize footing or cause injury. Because decomposition weakens wood structure over time, what appears solid may fracture under pressure. Seasonal changes reshape ground conditions significantly. During wet seasons, rising water tables soften soils further. Flooding spreads sediment unevenly. During drier periods, surfaces may firm slightly, yet underlying layers remain saturated. These seasonal cycles mean that terrain familiarity from previous visits does not guarantee identical conditions later. Temperature affects soil behaviour as well. In colder climates, partial freezing may stabilise surfaces temporarily. Thaw periods reverse that stability quickly. Freeze-thaw cycles also break down soil structure, increasing long-term softness. Visitors unfamiliar with these cycles may misjudge seasonal accessibility. Slope gradients, though often subtle in wetlands, influence water flow and soil firmness. Slight elevations drain marginally better, supporting firmer vegetation. Depressions accumulate water, creating softer zones. Learning to recognize these microtopographic differences helps predict safer routes, though practice is required. Peat depth varies widely among swamps. Some areas have shallow organic layers over mineral soil, while others contain meters of accumulated peat. Deep peat behaves differently under load, sometimes shifting laterally rather than compressing vertically. That movement can destabilize footing even when sinking remains limited. Gas accumulation occasionally occurs within saturated soils. Anaerobic decomposition produces methane, carbon dioxide and other gases that form bubbles trapped in peat. When disturbed, these pockets may release suddenly, altering local soil consistency. While rarely dangerous in open environments, they contribute to unpredictability. Water chemistry interacts with soil composition. High tannin concentrations from decomposing plant material affect water colour, but also influence microbial activity. Certain bacteria produce compounds that alter sediment cohesion. These biochemical processes occur continuously, subtly reshaping ground conditions. Human modification has altered some swamp terrains. Drainage attempts, logging or infrastructure development may leave residual channels, compacted zones, or disturbed sediment layers. These anthropogenic features complicate natural patterns. Old drainage ditches, for example, may fill partially but remain softer than surrounding soil. Transportation infrastructure in wetlands illustrates adaptive engineering responses. Raised boardwalks, floating platforms and causeways distribute weight across larger areas. These structures prevent excessive compression while allowing water flow underneath. Their design reflects lessons learned about wetland soil mechanics. Footwear choice influences movement efficiency greatly. Wide-soled boots distribute weight better than narrow shoes. Waterproof materials protect against prolonged moisture exposure. Gaiters help prevent mud ingress. Even with proper equipment, progress remains slower than on dry land. Energy expenditure during swamp travel often exceeds expectations. Each step requires balance correction, extraction effort from mud, and attention to obstacles. Over time, this increased effort contributes to fatigue. Fatigue, in turn, reduces attention to footing, increasing risk of slips or missteps. Hydration needs rise under such conditions. Warm, humid air impairs cooling, and physical exertion increases fluid loss. Carrying adequate potable water becomes essential because surrounding water usually requires treatment before safe consumption. Navigation challenges intensify when ground instability limits route options. Straight-line travel may prove impractical. Detours around deep mud, water channels, or dense vegetation extend travel time. Planning must account for these inefficiencies. Emergency response logistics in swamps reflect terrain difficulty. Search and rescue operations often require specialized equipment like airboats, amphibious vehicles, or helicopters. Ground teams move slowly. Communication infrastructure may be limited by vegetation density and moisture effects on electronics. Wildlife behavior sometimes correlates with ground stability. Larger animals often follow slightly elevated ridges or established paths. Observing these patterns can provide clues to firmer terrain. However, relying solely on animal trails carries its own uncertainties. Scientific mapping of wetlands uses technologies like LIDAR and ground-penetrating radar to assess elevation and subsurface structure. These tools reveal subtle variations invisible at ground level. Such data informs conservation planning, infrastructure development, and hazard assessment. Environmental education increasingly includes wetland terrain awareness. Outdoor programs teach recognition of vegetation indicators, soil firmness testing, and safe movement techniques. Awareness reduces accident rates while encouraging responsible exploration. Peatlands, a subset of swamp environments, store significant global carbon reserves. Disturbance through drainage or excessive foot traffic accelerates decomposition, releasing stored carbon. This ecological dimension adds another reason for cautious interaction. Agricultural conversion of wetlands historically involved drainage to stabilize soils. While effective for farming, such conversion often reduces biodiversity and alters hydrological cycles. Restoration projects sometimes aim to re-establish natural water levels, reversing earlier modifications. Climate change influences swamp ground conditions, altered rainfall patterns, rising temperatures, and sea level changes affect water tables. Some wetlands expand, others dry partially. These shifts alter soil stability over time. Public safety messaging increasingly emphasizes that swamps rarely present dramatic hazards, but consistently present subtle ones. Gradual sinking, fatigue, navigation difficulty, and environmental exposure collectively pose greater risk than sudden catastrophic events. Photography and media representation sometimes emphasize visual drama without conveying terrain mechanics. Viewers may underestimate effort required to move safely through wetlands. Balanced communication helps align expectation with reality. Researchers working regularly in swamps often develop intuitive understanding of ground cues. Plant species indicating depth, subtle colour changes suggesting firmer soil, water surface patterns hinting at flow. That expertise builds over repeated exposure. Even with experience, unpredictability remains part of the environment. Continuous biological activity, weather variation, and hydrological changes ensure no two visits replicate exactly. Maintaining caution remains essential. Understanding the mechanics of mud, peat, and hidden water channels clarifies why swamps challenge mobility consistently. and that physical instability interacts with biological factors too, particularly microorganisms and disease vectors that thrive in standing water, which brings attention naturally toward how seemingly calm water surfaces can carry health risks not immediately visible. Water that looks calm often suggests safety. A smooth surface, no visible current, maybe a few floating leaves, perhaps birds moving quietly along the edge. In many environments, still water simply means a pond or lake with limited movement. In swamp ecosystems, however, stillness carries additional implications because slow or stagnant water creates conditions where microorganisms, parasites, and disease vectors can thrive in ways that are not always obvious at first glance. The danger rarely comes from the water itself in a dramatic sense. It comes from what lives in it, what breeds there, and what prolonged exposure can do to the human body. One fundamental factor is oxygen content. Moving water mixes with air continuously, maintaining relatively higher dissolved oxygen levels. Still swamp water often has lower oxygen levels because decomposition consumes oxygen faster than diffusion replaces it. That low oxygen environment favours certain bacteria and microorganisms adapted to anaerobic conditions. Many of these microbes play essential ecological roles, breaking down organic material and recycling nutrients, but some can also affect human health if exposure occurs through ingestion, open wounds, or prolonged skin contact. Waterborne bacteria such as Leptospira provide one example. These bacteria can survive in warm, stagnant water contaminated by animal urine. Human infection, called leptospirosis, can occur when the bacteria enter through cuts in the skin or mucous membranes. Symptoms range from mild flu-like illness to more serious complications affecting the liver or kidneys. The infection is treatable, but awareness matters because exposure risk increases in environments where humans wade through untreated standing water. Another concern involves protozoan parasites. Organisms like Giardia or Cryptosporidium sometimes persist in surface water, especially where animal populations concentrate. These microscopic parasites can cause gastrointestinal illness if ingested. Filtration or purification usually removes them effectively, yet untreated water consumption remains a common cause of illness during outdoor travel in wetlands. Fungal organisms also benefit from constant moisture. Certain fungi colonize wet soils, decaying vegetation, or shallow water edges. Skin exposure during prolonged wading can lead to fungal infections, particularly when footwear stays damp for extended periods. These infections are usually manageable, but uncomfortable, and sometimes persistent if not addressed promptly. Beyond microorganisms directly in the water, swamp conditions strongly support disease vectors, especially insects. Mosquitoes represent the most widely recognized example. Standing water provides ideal breeding habitat because larvae develop in calm aquatic environments without strong currents. Different mosquito species carry different pathogens including malaria parasites, dengue viruses, West Nile virus, Zika virus, and others depending on geographic region. Modern public health programs reduce transmission risk substantially, yet wetlands remain key ecological reservoirs for mosquito populations. Ticks form another vector group associated with humid wetland environments. Dense vegetation and abundant wildlife hosts create favourable conditions. Ticks can transmit bacterial infections like Lyme disease, as well as viral and parasitic illnesses. Preventive measures, including protective clothing and regular inspection, significantly reduce risk, but awareness remains important. Snails in freshwater swamps sometimes host parasitic worms such as schistosomes. These parasites can penetrate human skin during water contact in certain tropical regions. The resulting infection, schistosomiasis, affects millions globally. It is region-specific, so risk depends strongly on location, yet it illustrates how aquatic organisms can participate indirectly in disease cycles. Algal blooms occasionally develop in stagnant swamp waters, particularly when nutrient levels rise. Some algae produce toxins harmful to humans and animals. Direct ingestion or inhalation of aerosolized droplets can cause symptoms ranging from mild irritation to more serious neurological or hepatic effects. Monitoring programs track such blooms in many regions. Another microbial aspect involves decomposition gases. Anaerobic bacteria break down organic material, producing methane, hydrogen sulfide, and carbon dioxide. Outdoors, these gases usually disperse quickly. However, localized pockets may produce noticeable odor or mild irritation. Hydrogen sulfide, recognizable by its sulfurous smell, can cause discomfort at higher concentrations, though dangerous levels rarely persist in open swamp environments. Water contact over extended periods softens skin, increasing susceptibility to infection. Cuts, abrasions, or insect bites provide entry points for bacteria. Maintaining dry clothing where possible and cleaning wounds promptly helps prevent complications. This practical consideration often matters more than dramatic hazards. Climate influences microbial activity strongly. Warm temperatures accelerate reproduction rates for many microorganisms. Tropical and subtropical swamps therefore often present higher disease exposure potential compared with cooler wetlands. Seasonal rainfall patterns further affect vector populations by expanding or contracting breeding habitat. Human history offers many examples of wetlands influencing disease patterns. Malaria once shaped settlement decisions in parts of Europe and North America before modern control methods reduced prevalence. Drainage projects historically aimed partly at reducing mosquito breeding sites. While those projects altered ecosystems significantly, they illustrate how strongly wetlands intersect with public health considerations. Today, integrated management approaches balance conservation with disease control. Biological mosquito control methods, habitat management, and public education aim to reduce risk while preserving ecological function. Wetlands remain vital ecosystems, so strategies focus on mitigation rather than elimination. Water filtration technology has improved significantly. Portable filters, ultraviolet purifiers, and chemical treatments provide reliable protection for individuals working or travelling in wetlands. Proper use reduces ingestion risk effectively. Education about these tools forms part of outdoor safety training. Protective clothing also plays a role. Waterproof boots reduce prolonged skin contact with contaminated water. Long sleeves and insect repellent decrease vector exposure. Lightweight, breathable fabrics help manage heat while maintaining coverage. These measures combine practical comfort with health protection. Wildlife interactions intersect with microbial risk as well. Animals often act as reservoir hosts for pathogens without showing symptoms. Rodents, birds, reptiles, and mammals all participate in complex ecological disease cycles. Direct contact with wildlife or contaminated surfaces increases exposure potential, so maintaining respectful distance benefits both humans and animals. Flood events can temporarily expand disease risk. Rising water spreads microorganisms into new areas, mixes waste sources, and increases vector breeding habitat. Post-flood conditions often require public health monitoring. Wetlands naturally experience seasonal flooding, but extreme weather events can intensify effects. Water chemistry affects microbial survival. Salinity, pH, temperature, and nutrient availability all influence which organisms dominate. Coastal mangrove swamps differ microbiologically from freshwater forested wetlands. Understanding regional characteristics helps assess realistic risk levels. Scientific research continues exploring wetland microbiomes. Environmental DNA sampling reveals previously unknown microbial diversity. Many organisms discovered perform beneficial ecological functions, including pollutant breakdown. Some even hold medical research potential. This complexity highlights that wetlands are not inherently hazardous. Rather, they host diverse biological communities with both positive and negative implications. Public perception sometimes exaggerates microbial risk due to unfamiliarity. Balanced understanding recognizes genuine hazards without assuming constant danger. Most swamp visits, when properly prepared, proceed safely. Problems arise primarily when precautions are ignored or environmental conditions are underestimated. Tourism infrastructure often incorporates this knowledge. Boardwalks, observation platforms, and guided tours allow wetland appreciation without direct water contact. Educational signage explains ecological processes and safety considerations simultaneously. Climate change introduces additional variables. Rising temperatures, altered precipitation patterns, and shifting wildlife distributions influence disease ecology. Some vector species expand into new regions. Monitoring programs track these trends to inform public health responses. Occupational exposure remains relevant for researchers, conservation workers, and local communities whose livelihoods involve wetlands. Vaccination programs, protective equipment, and training reduce occupational health risks effectively. Psychological perception of invisible threats differs from visible hazards like unstable ground or large wildlife. Microbial risks require conceptual understanding rather than immediate visual cues. Education helps translate scientific knowledge into practical behaviour. Medical treatment for most waterborne infections exists, especially when diagnosed early. Prompt attention to symptoms following swamp exposure improves outcomes. Health professionals often consider environmental exposure history during diagnosis. Water sampling in wetlands provides valuable environmental indicators. Scientists monitor bacterial counts, nutrient levels, and chemical composition to assess ecosystem health. These data support conservation planning and public safety guidelines. Local knowledge often proves invaluable. Communities living near wetlands develop practical understanding of seasonal disease patterns, safe water sources, and protective practices. Integrating traditional knowledge with scientific research enhances overall safety. Ultimately, still water in swamp ecosystems represents both ecological richness and potential health risk, recognizing that dual nature allows informed interaction rather than avoidance or complacency. Calm surfaces do not necessarily indicate safety, yet they do not guarantee danger either. Context, preparation, and awareness determine outcomes. And as microbial life thrives quietly beneath the surface, insects that depend on that water begin their own life cycles there too, particularly mosquitoes whose populations shape both ecological balance and human experience in wetlands, which naturally leads toward understanding how these small creatures influence entire regions far beyond the immediate swamp boundary. When people think about swamps and insects, mosquitoes usually come to mind first, and that association exists for good reason. Wetlands provide ideal breeding conditions for many insect species, but mosquitoes in particular benefit from the combination of standing water, warm temperatures, abundant organic material, and relatively sheltered environments. These conditions allow populations to grow rapidly, sometimes to densities that influence human settlement patterns, economic activity, public health policy, and even historical events. What seems like a small insect issue on the surface can actually shape entire regions over long periods. The mosquito life cycle explains why swamps support them so effectively. Female mosquitoes lay eggs in or near standing water. Those eggs hatch into larvae that live entirely in water, feeding on microorganisms and organic particles. The larval stage requires calm water because strong currents would disperse or damage them. Swamps with slow water movement and plentiful nutrients from decomposing vegetation create optimal nursery conditions. After several growth stages, larvae become pupae and then emerge as flying adults. Warm temperatures accelerate this cycle, allowing multiple generations within a single season. Not all mosquitoes behave the same way. Different species prefer slightly different water conditions. Some favour clean standing water, others tolerate highly organic or even polluted environments. Certain species remain close to breeding sites, while others travel considerable distances. Understanding species variation matters because disease transmission potential varies widely between species. Historically, mosquito-borne diseases influenced where humans could live comfortably. Before modern mosquito control methods, some swamp-rich regions experienced high malaria prevalence. Communities adapted by building homes on raised platforms, using bed nets, or limiting activity during peak mosquito hours. In certain cases, large-scale drainage projects aimed partly at reducing mosquito habitat. Those projects changed ecosystems significantly, sometimes improving public health, but also reducing biodiversity and natural flood protection. Malaria remains one of the most well-known mosquito-borne diseases globally. It is caused by Plasmodium parasites transmitted by specific Anopheles mosquito species. Swamp environments historically provided extensive breeding grounds for these mosquitoes. Modern control strategies, including insecticide-treated nets, environmental management and medical treatment, have reduced impact in many areas, yet ecological conditions still influence disease distribution. Other diseases associated with swamp mosquito populations include dengue fever, West Nile virus, chikungunya, Zika virus, and yellow fever. Each disease involves different mosquito species and geographic ranges. Climate, water availability, and vegetation all affect transmission dynamics. Public health agencies monitor mosquito populations closely in wetland regions to anticipate outbreaks. Beyond disease transmission, mosquito density alone influences human experience. Persistent biting interferes with outdoor work, recreation, and habitation. Protective clothing, repellents, and screen structures help, but extremely dense populations can still affect daily comfort. Economic activities such as agriculture, forestry, and tourism sometimes adjust schedules or infrastructure design accordingly. Mosquitoes also occupy important ecological roles. Their larvae contribute to aquatic food webs, feeding fish, amphibians, and other insects. Adult mosquitoes serve as prey for birds, bats, spiders, and other predators. Eliminating mosquitoes entirely would disrupt those relationships. Modern control strategies often focus on reducing disease-carrying species rather than total eradication. Biological control methods illustrate this approach, introducing fish species that consume mosquito larvae, encouraging dragonfly populations, or using bacteria that target mosquito larvae specifically can reduce populations without widespread ecological disruption. Such methods require careful planning to avoid unintended consequences. Chemical control methods exist too, including larvicides and adult insecticides. These tools can reduce mosquito populations effectively during outbreaks, but must be used cautiously to minimize environmental impact. Overuse can affect non-target species and contribute to insecticide resistance. Urban development near wetlands sometimes unintentionally increases mosquito habitat. Artificial containers, drainage ditches, and poorly managed water systems create additional breeding sites. Integrated urban planning now often includes wetland management strategies that consider mosquito ecology alongside environmental preservation. Climate change adds complexity. Rising temperatures expand the geographic range suitable for certain mosquito species. Altered rainfall patterns create new standing water habitats. Regions previously unaffected by specific mosquito-borne diseases may begin experiencing occasional cases. Monitoring programs track these shifts to guide public health responses. Humidity, common in swamp regions, also affects mosquito survival. High humidity prolongs adult mosquito lifespan, increasing chances for disease transmission because pathogens often require time to develop inside the mosquito before becoming transmissible. Dry conditions reduce mosquito survival, which partly explains seasonal variation in disease risk. Human behavior influences exposure as well. Peak mosquito activity often occurs at dawn and dusk. Awareness of these patterns allows scheduling adjustments. Lighting choices, clothing color, and scent also affect mosquito attraction to some degree, though research on these factors continues. Swamp vegetation provides resting sites for adult mosquitoes during daytime. Dense foliage protects them from predators and environmental stress. Managing vegetation around human settlements can reduce resting habitat without altering broader ecosystem structure significantly. Water chemistry influences mosquito breeding preferences. Some species prefer fresh water, others tolerate brackish conditions. Nutrient levels affect microbial food availability for larvae. Environmental monitoring helps predict where populations may increase. Wetland conservation efforts sometimes integrate mosquito management from the start. Designing water flow patterns that reduce stagnant pockets, maintaining predator habitats, and monitoring seasonal changes all contribute to balanced ecosystems that minimize disease risk. Cultural responses to mosquitoes vary globally. Some communities develop traditional plant-based repellents or architectural designs that reduce exposure. Others incorporate seasonal migration patterns tied partly to insect density. These practices reflect long-term adaptation to wetland environments. Tourism infrastructure in swamp regions often includes mosquito mitigation measures, screened accommodations, repellents, visitor education, and guided tours scheduled during lower activity periods. Such planning allows people to experience wetlands while maintaining comfort and safety. Scientific research into mosquito genetics has opened possibilities for targeted population control. Techniques like sterile insect release or gene drive systems aim to reduce disease-carrying species selectively. Ethical and ecological considerations remain central in evaluating these methods. Public education plays a crucial role. Understanding mosquito life cycles encourages simple preventive actions, such as eliminating small standing water containers near homes. Awareness campaigns often link local wetland ecology with personal protective measures. Economic costs associated with mosquito-borne diseases extend beyond healthcare. Lost productivity, tourism decline, agricultural disruption, and infrastructure investment all factor into regional planning. Recognizing wetlands as both ecological assets and disease ecology components informs balanced policy. Environmental monitoring technologies have advanced considerably. Satellite imagery identifies standing water changes. Drone surveys map vegetation density. Environmental DNA sampling detects mosquito species presence. These tools improve predictive capacity. Personal protective technology continues evolving as well. Improved repellents, lightweight protective fabrics, and spatial repellent devices enhance comfort during wetland activities. Research aims to increase effectiveness while minimizing environmental impact. Despite their reputation, mosquitoes rarely act aggressively without stimulus. Carbon dioxide exhalation, body heat, and certain chemical cues attract them. Understanding these triggers informs protective strategies. Educational programs for outdoor workers emphasize layered protection, clothing, repellents, awareness of peak activity times, and prompt treatment of bites. These measures significantly reduce disease transmission risk. Community-based mosquito control often proves most effective. Local participation in monitoring, habitat management, and education creates sustained results. Collaboration between public health agencies, conservationists, and residents supports balanced outcomes. Wildlife interactions add another dimension. Migratory birds can transport mosquito-borne pathogens across regions. Wetlands serve as stopover habitats, influencing disease ecology on broader geographic scales. Insects beyond mosquitoes also thrive in swamps. Biting flies, midges, and other arthropods contribute to the overall insect environment. While not always disease vectors, they affect comfort and ecological dynamics. Scientific understanding continues evolving. Researchers study how wetland restoration influences mosquito populations, how climate variables alter breeding cycles, and how ecosystem balance affects disease transmission. Recognizing mosquitoes as both ecological participants and public health factors allows nuanced understanding. Swamps do not simply produce pests, They host complex biological communities. Human interaction requires awareness rather than blanket avoidance, and as attention shifts from insects to larger swamp inhabitants, it becomes clear that dense vegetation, shallow water, and limited visibility also create ideal conditions for ambush predators, animals whose presence is often subtle until close proximity reveals it, which naturally leads toward examining how larger wildlife contributes to the perception of swamps as challenging ecosystems. Dense vegetation, shallow water, filtered light, and constant background sound combine to make swamps particularly well suited for ambush predators. These ecosystems offer cover, concealment, stable water access, and prey concentration, all conditions that many reptiles and mammals exploit effectively. From a distance, the environment may appear calm and quiet, but the same features that make it visually appealing also allow predators to remain unnoticed until very close range. That reality does not mean swamps are inherently hostile places full of aggressive animals waiting for humans. Most predators avoid human contact whenever possible. The issue is visibility, unpredictability, and shared space in an environment where humans do not move as naturally as the resident wildlife. Reptiles are often the first large predators associated with swamp habitats. Crocodilians, including alligators, crocodiles, and caimans, depending on geographic region, thrive in wetland environments. Their physiology suits slow water perfectly. Eyes and nostrils positioned high on the head allow them to remain mostly submerged while observing surroundings. Their coloration blends with muddy water and vegetation. Motion detection is extremely sensitive. These adaptations allow them to hunt efficiently without expending unnecessary energy. Most crocodilian species show little interest in humans as prey. They generally prefer fish, birds, smaller mammals, and occasionally larger animals that approach water edges. Incidents involving humans tend to occur when people inadvertently approach nests, feed wildlife intentionally, or enter water where visibility is poor. Education campaigns in regions with crocodilian populations emphasize maintaining distance, avoiding swimming in unclear waters, and respecting posted warnings. These measures significantly reduce incidents. Large snakes also occupy swamp environments worldwide. Species vary widely depending on location: pythons in tropical wetlands, anacondas in South American swamps, water moccasins in North America, and various other semi-aquatic snakes elsewhere. These reptiles benefit from camouflage, slow water movement, and abundant prey. Like crocodilians, they usually avoid humans unless threatened or cornered. Most bites occur when snakes are stepped on accidentally or handled intentionally. Snake perception often exaggerates risk because of cultural narratives. Statistically, most swamp visits do not involve snake encounters. However, awareness matters because vegetation density reduces visibility. Protective footwear, careful stepping, and avoidance of reaching blindly into vegetation lower encounter risk considerably. Mammalian predators also use swamp environments effectively. Big cats such as jaguars, leopards, or tigers in certain regions hunt near wetlands because prey species congregate there. In North America, bobcats occasionally use swamp edges for hunting. In Africa, some lion populations incorporate wetland areas into their territories. These predators rely heavily on stealth, using vegetation cover and low visibility conditions. Again, human encounters with large mammalian predators remain rare. Most incidents occur when animals feel threatened, surprised, or habituated to human presence due to feeding or encroachment. Wildlife management agencies emphasize not feeding animals, maintaining distance, and understanding animal behavior cues. Semi-aquatic mammals like otters, mink, and muskrats also inhabit swamps. These species rarely pose danger to humans, but can behave defensively if approached too closely, especially during breeding seasons. Their presence often indicates healthy wetland ecosystems. Wild pigs or boars sometimes inhabit swamp regions, particularly where dense vegetation provides cover. These animals can be unpredictable if startled. While not traditional predators, their defensive behavior can cause injury. Avoidance and awareness remain key safety principles. Birds of prey contribute another dimension. Some raptors hunt fish or small mammals in wetlands. While not dangerous to adult humans, nesting birds may defend territories vigorously. Awareness of nesting seasons and maintaining respectful distance prevents conflicts. Predator hunting strategies often rely on patience rather than pursuit. Remaining still, blending into surroundings, and waiting for prey movement conserves energy. Swamp environments enhance these strategies because sound travels unpredictably. Vegetation obscures outlines, and water dampens vibrations. Humans unfamiliar with these cues may overlook nearby animals simply because they do not expect effective concealment. Light conditions influence predator success as well. Diffuse sunlight under canopy reduces sharp shadows. Overcast conditions common in humid wetlands further flatten visual contrast. Predators adapted to these lighting conditions detect movement more effectively than shapes. Sudden human movement may attract attention, even when coloration blends with surroundings. Water clarity plays a role too. Tannin-stained or sediment-rich water conceals submerged animals. Crocodilians and large fish often remain nearly invisible until they move. Maintaining distance from water edges where visibility is limited reduces risk. Seasonal factors affect predator behavior. Breeding seasons may increase territoriality. Drought periods concentrate prey around remaining water sources, increasing predator activity locally. Flood seasons disperse animals across larger areas. Understanding these cycles helps interpret wildlife presence realistically. Sound cues often provide early warning. Splashing, rustling vegetation, or bird alarm calls may indicate nearby animal movement. Learning to interpret such cues improves situational awareness. Many experienced field researchers rely on auditory information as much as visual observation. Smell also plays a role. Some predators mark territory with scent. Humans may detect musky odors indicating recent animal presence. Wind direction influences scent dispersion, adding another environmental variable. Human movement patterns differ markedly from wildlife. Upright posture, clothing color, and equipment noise distinguish humans clearly once animals detect them. Most predators choose avoidance rather than confrontation when given opportunity. Calm, steady movement without sudden gestures reduces perceived threat. Feeding wildlife creates artificial risk. Animals accustomed to human food sources may lose natural avoidance behavior. Such habituation increases encounter probability. Responsible wildlife interaction guidelines strongly discourage feeding in wetland environments. Habitat fragmentation influences predator behavior too. Urban expansion near wetlands sometimes compresses wildlife territories. Animals may venture closer to human activity out of necessity. Balanced land management helps maintain natural separation. Conservation programs increasingly emphasize coexistence strategies. Public education about wildlife behavior, habitat preservation, and safe observation practices supports both human safety and species protection. Technological advances assist monitoring predator populations. Camera traps, GPS collars, and environmental DNA sampling provide data without constant human presence. These tools inform management decisions and public advisories. Cultural perspectives on predators vary widely. Some communities revere certain animals, incorporating them into folklore or conservation traditions. Others historically viewed them primarily as threats. Modern ecological understanding often integrates cultural knowledge with scientific research. Tourism infrastructure in swamp regions frequently includes guided observation. Experienced guides understand animal behavior patterns and safe viewing distances. Guided visits reduce risk while enhancing educational value. Emergency response planning in wetland regions considers wildlife presence. Training for park rangers, rescue teams, and local authorities includes wildlife encounter protocols. Preparedness improves outcomes when incidents occur. Media portrayal sometimes exaggerates predator aggression for dramatic effect. Balanced information helps replace fear with informed respect. Understanding animal motivations reduces unnecessary anxiety while maintaining appropriate caution. Scientific research highlights that predator presence often indicates ecosystem health. Apex predators regulate prey populations, maintaining ecological balance. Their existence reflects functioning food webs rather than inherent environmental hostility. Acoustic monitoring studies show that predator vocalizations contribute to swamp soundscapes. These sounds provide information to both prey species and human observers willing to listen carefully. Environmental ethics discussions increasingly consider human responsibility in predator encounters. Habitat preservation, responsible recreation, and wildlife respect reduce conflict likelihood. Understanding predator ecology helps contextualize risk realistically. Awareness, preparation, and respect usually suffice to ensure safe coexistence. Panic or ignorance often create greater danger than the animals themselves. As attention shifts from larger predators to smaller, but sometimes more immediately hazardous species, it becomes clear that venomous snakes, spiders, and other less conspicuous creatures occupy the same dense environments, often harder to detect precisely because of their size, coloration, and quiet behavior, which leads naturally into examining how these smaller residents contribute to swamp safety considerations. If larger predators tend to capture attention because of size and visibility, smaller venomous animals often represent a quieter category of risk in swamp environments. They rarely announce themselves clearly. Many rely on camouflage, stillness, or nocturnal activity. Encounters usually happen not because these animals seek humans out, but because humans accidentally move into their space without noticing. In wetlands where visibility is limited by vegetation, water turbidity, and filtered light, detecting small animals becomes more challenging, which is why understanding their habits matters more than fearing them. Snakes probably generate the strongest reaction among people entering swamp habitats. Many wetland regions host venomous species alongside non-venomous ones, and distinguishing between them quickly is not always easy. Water moccasins in North America, certain cobras in Asian wetlands, various vipers in tropical swamps, and other region-specific species demonstrate how reptiles adapt to semi-aquatic conditions. Their coloration often matches muddy water, fallen leaves, or shaded vegetation, making them difficult to spot until very close. Despite common perception, most venomous snakes prefer avoidance over confrontation. They conserve energy by remaining still rather than chasing large animals. Bites usually occur when a snake feels threatened, stepped on, or handled. Swamps increase accidental encounter probability because people often step where they cannot see clearly. Thick grass, floating debris, and shallow murky water obscure visual cues that would otherwise warn of a snake's presence. Footwear becomes particularly important under these conditions. Thick boots provide some protection against fangs. Long pants reduce skin exposure. Slow, deliberate steps give animals time to move away. Many field researchers adopt a walking rhythm that includes scanning ahead with each step rather than focusing only on immediate footing. This reduces surprise encounters significantly. Spiders form another group that thrives in humid wetland environments. Most spiders are harmless to humans, and many play valuable ecological roles by controlling insect populations. However, certain venomous species inhabit swamp regions globally. Their bites can cause pain, swelling, or systemic symptoms depending on species and individual sensitivity. Like snakes, spiders usually bite defensively when trapped against skin or disturbed suddenly. Wet conditions favour spiders that build webs near water surfaces or in dense vegetation. Some species live under bark, within hollow logs, or among plant roots. Reaching blindly into vegetation, sitting on fallen logs without inspection, or storing gear directly on the ground increases contact likelihood. Simple precautions such as shaking out clothing and checking resting spots reduce risk. Scorpions appear in some swamp-adjacent regions, particularly where drier elevated ground borders wetlands. While not strictly aquatic, they may occupy nearby vegetation. Venom potency varies widely among species. Awareness of local fauna helps guide appropriate caution. Aquatic invertebrates sometimes receive less attention but can also cause problems. Certain freshwater snails host parasitic organisms, while others may irritate skin. Leeches, common in some tropical wetlands, rarely transmit disease but can cause discomfort or minor blood loss. Their presence often surprises newcomers unfamiliar with wetland fauna. Insect stings represent another category. Wasps, hornets, and ants may nest in vegetation near water. Flooding occasionally displaces nests, leading to temporary concentration in new areas. Disturbing such nests inadvertently can result in multiple stings. Protective clothing and careful observation minimize encounters. Visibility remains a central theme. Swamp lighting conditions often reduce contrast. Brown water reflects sky colours, leaves float on surfaces, movement detection becomes harder. Animals adapted to these conditions exploit visual ambiguity effectively. Humans must compensate with slower movement and attention to detail. Temperature influences venomous species activity. Many reptiles and insects become more active in warm conditions. Seasonal awareness helps anticipate encounter likelihood. Cooler periods generally reduce activity, though not eliminate it. Human scent and vibration alert many animals before visual detection occurs. Moving steadily rather than abruptly allows animals to retreat. Loud, erratic movement may provoke defensive responses. Calm, predictable behaviour benefits both parties. Cultural attitudes toward venomous animals vary widely. Some societies incorporate traditional knowledge about safe coexistence, including seasonal patterns, habitat preferences, and first aid responses. Integrating such knowledge with modern science improves safety outcomes. Medical preparedness matters in regions where venomous species occur. Knowing nearest medical facilities, carrying communication devices, and understanding basic first aid procedures contribute to effective response if a bite or sting occurs. Anti-venom availability varies geographically, so local knowledge remains important. Scientific research continues refining understanding of venom composition and treatment. Many venoms contain complex proteins studied for pharmaceutical applications. This research highlights that animals perceived primarily as threats also contribute to medical advances. Education programs often emphasize identification skills. Learning distinguishing features between venomous and non-venomous species reduces unnecessary fear and inappropriate reactions. Quick identification also supports appropriate medical response if needed. Media portrayals sometimes exaggerate aggressiveness of venomous animals. Documentaries increasingly focus on behaviour realism rather than sensationalism, helping reshape public perception toward informed respect. Protective technology has improved as well. Lightweight snake gaiters, insect-resistant fabrics, and improved repellents enhance safety without excessive discomfort. These innovations make wetland exploration more accessible while maintaining caution. Environmental changes influence venomous species distribution. Habitat loss elsewhere may push animals toward remaining wetlands. Climate shifts can expand or contract geographic ranges. Monitoring programs track these patterns to inform public guidance. Emergency response protocols in wetland areas include training on venomous animal encounters. Park staff, researchers, and guides learn species behaviour, avoidance techniques, and first aid. Such training significantly reduces incident severity. Wildlife conservation considerations intersect with safety. Protecting venomous species maintains ecological balance. Education encourages coexistence rather than eradication. Balanced messaging emphasizes avoidance and respect. Children and inexperienced visitors benefit from structured introduction to wetlands. Guided programs teach observation skills, appropriate clothing choices, and safe movement habits early, reducing long-term risk. Scientific field stations in swamp regions often maintain incident records. Data analysis informs updated safety guidelines. Evidence-based recommendations replace anecdotal fear. Communication technology aids safety as well. GPS devices, satellite messengers, and mobile apps provide location tracking in remote wetlands where traditional signals fail. Rapid communication improves response times. Ultimately, venomous residents form part of broader swamp biodiversity. Awareness, preparation, and calm behaviour reduce encounter likelihood dramatically. Fear alone offers little protection. Understanding provides practical benefit. And while animals often draw attention because of movement or potential danger, plants themselves contribute hazards too, sometimes through toxins, irritants, or structural obstacles, which naturally shifts focus toward how vegetation in swamp environments presents its own set of risks alongside the animals living among it. When people think about danger in natural environments, animals usually come to mind first. Movement draws attention. Teeth, claws, or venom seem obvious. Plants, by contrast, appear stationary and harmless at first glance. In swamp ecosystems, that assumption can be misleading. Wetland vegetation has evolved a wide range of defences against herbivores, competition, flooding stress, and microbial attack. Some of those adaptations create very practical hazards for humans moving through dense waterlogged terrain. The risks rarely involve dramatic poisoning scenarios, but irritation, injury, infection, risk, and mobility obstruction occur often enough to deserve attention. One of the most immediate plant-related hazards in swamps involves physical structure. Many wetland plants grow aggressively because water availability removes one major growth limitation. Trees, reeds, grasses, vines, and shrubs compete intensely for light. That competition produces dense vegetation with thorns, sharp leaf edges, rigid stems, and tangled root systems. Moving through such growth requires constant adjustment. Clothing snags, skin contacts rough surfaces. Balance becomes harder to maintain when roots and stems cross typical walking paths. Some swamp grasses develop silica-reinforced edges that feel almost blade-like. Contact can cause small cuts that may not seem serious initially. However, warm, humid conditions promote bacterial growth. Minor abrasions become potential infection entry points. Cleaning cuts promptly matters more in wetlands than in dry environments for that reason. Thorn-bearing plants appear frequently along swamp edges where light penetration is greater. Species such as certain palms, berry bushes, or wetland-adapted shrubs use thorns as herbivore deterrents. Thick clothing reduces skin injury risk, but exposed areas like hands or face may still encounter sharp points when navigating dense growth. Vines present a different structural hazard. Many swamp vines climb trees or sprawl across the ground, forming tangled networks. Some lie just above water level, difficult to see until encountered. Stepping into a vine loop can destabilize footing. Overhead vines catch on equipment or clothing. Slow, deliberate movement reduces entanglement risk. Beyond structural defences, chemical plant defences play a significant role. Numerous wetland plants produce irritant sap, oils, or microscopic hairs that cause skin reactions. Contact dermatitis from plants like poison ivy, poison sumac, or region-specific equivalents occurs commonly in certain swamp regions. These plants often grow exactly where moisture and partial sunlight meet, places humans tend to traverse. The reaction mechanism typically involves immune system response to plant-produced compounds such as urushiol oils. Symptoms range from mild redness to pronounced itching and blistering. Washing exposed skin soon after contact reduces severity. Awareness of plant appearance helps avoidance. Some aquatic or semi-aquatic plants produce compounds that irritate eyes or mucous membranes if touched, and then transferred by hand contact. Wearing gloves when handling vegetation during research or travel reduces exposure significantly. Toxic ingestion risk exists too, although it rarely arises accidentally unless someone consumes unfamiliar plants. Certain swamp berries, roots, or leaves contain alkaloids, glycosides, or other toxic compounds. Foraging without proper botanical knowledge presents obvious hazards. Education programs emphasize positive identification before consumption. Fungi associated with wetland plants add another layer. Mushrooms growing on decaying wood or moist soil vary widely in edibility. Some are harmless, others toxic. High moisture accelerates fungal growth, so wetlands often host abundant fungal diversity. Again, knowledge prevents risk. Plant decomposition in swamps produces tannins that stain water dark brown. While not toxic themselves, tannins indicate organic decomposition processes that often coincide with microbial populations unsuitable for direct water consumption. Visual cues like tea-coloured water remind experienced visitors to treat water before drinking. Root systems create terrain hazards independent of toxicity. Trees growing in saturated soil frequently develop lateral roots near the surface. These roots may be partially submerged or covered by leaf litter. Stepping on them can lead to slips because wet bark becomes slick. Roots also create uneven ground height variations. Floating vegetation mats deserve particular caution. In some wetlands, intertwined plants form buoyant layers over water. From above, they resemble solid ground. Weight distribution determines whether they support passage or collapse partially. Researchers often probe such surfaces with poles before stepping. Aquatic plants sometimes conceal open water channels. Thick lily pads or emergent grasses hide depth transitions. Someone walking through shallow water may suddenly encounter deeper pockets where vegetation masks visual cues. Maintaining balance during such transitions requires attention. Plant density influences navigation as well. Dense stands of reeds or shrubs limit visibility. Landmarks disappear quickly. Orientation becomes difficult. People unfamiliar with the terrain may circle unintentionally. Navigation tools help but must function under canopy cover. Humidity affects plant surfaces. Constant moisture keeps leaves, stems, and bark damp, increasing slipperiness. Foot placement on plant-covered surfaces requires caution, similar to walking on wet rock. Good traction footwear helps but does not eliminate risk entirely. Seasonal growth cycles change vegetation density dramatically. Wet seasons often bring rapid plant expansion. Paths used earlier in the year may become overgrown. Dry seasons reduce density somewhat but may expose different hazards like brittle stems or dried thorns. Plant-animal interactions influence hazard patterns too. Some animals nest in dense vegetation. Disturbing those areas can provoke defensive behaviour from insects, birds, or mammals. Observing animal signs before pushing through thick growth reduces surprise encounters. Human modification of wetlands sometimes introduces non-native plant species. Invasive plants may grow especially densely, altering visibility and terrain stability. Some invasive species also produce irritant chemicals unfamiliar to local populations. Fire ecology intersects with vegetation hazard occasionally. While wetlands usually resist fire due to moisture, drought conditions can dry surface vegetation temporarily. Dead plant material becomes brittle, increasing puncture risk from sharp stems. Ecological importance of swamp vegetation cannot be overstated. Plants stabilize soil, filter water pollutants, provide wildlife habitat, and contribute to carbon storage. Recognizing hazards does not diminish ecological value. It encourages respectful interaction. Protective strategies remain straightforward. Wearing long sleeves, durable pants, gloves when necessary, and appropriate footwear reduces exposure significantly. Carrying first aid supplies for minor cuts or rashes supports quick response. Educational signage in protected wetlands often identifies hazardous plant species. Guided tours highlight distinguishing features, helping visitors learn recognition skills. This approach replaces fear with knowledge. Scientific research into wetland plants continues uncovering beneficial uses as well. Some species produce compounds studied for pharmaceuticals. Others support traditional medicine practices in local communities. Hazard and benefit frequently coexist. Photography and observation from designated walkways minimize plant contact while allowing appreciation. Boardwalks protect both visitors and fragile vegetation. Their placement reflects careful ecological planning. Cultural narratives sometimes portray swamp plants as menacing obstacles. While dramatic, these portrayals overlook ecological complexity. Most plants simply follow evolutionary strategies for survival rather than actively fighting back. Climate change influences vegetation patterns too. Altered water levels, temperature shifts, and storm frequency affect plant distribution. Some species expand, others decline. These changes alter hazard patterns gradually. Water filtration by swamp vegetation benefits downstream ecosystems. Plants absorb nutrients, trap sediment, and break down pollutants. This service underscores why wetland conservation remains a priority despite access challenges. Local communities often possess detailed plant knowledge developed over generations. Collaboration between scientists and local residents enhances safety and conservation outcomes. Traditional ecological knowledge complements modern research. Ultimately, swamp vegetation shapes both beauty and difficulty in these ecosystems. Dense growth supports biodiversity while complicating human movement. Chemical defenses protect plants while occasionally irritating skin. Structural complexity stabilizes soil yet creates obstacles. And once plant density, humidity, and water exposure combine with climate conditions typical of wetlands, heat and moisture begin influencing human physiology directly, which leads naturally into understanding how temperature, humidity, and exhaustion interact to make swamp environments physically demanding, even without obvious external threats. When people imagine swamps, they often focus on water, vegetation, or wildlife first. But climate plays an equally important role in shaping how these environments feel and how demanding they become for anyone spending time there. Temperature alone rarely tells the whole story. Humidity, air movement, solar exposure, and ground moisture all interact in ways that influence how the human body regulates heat, uses energy, and maintains hydration. These factors combine gradually rather than dramatically, which is why exhaustion in swamp environments sometimes develops without immediate warning. Humidity is usually the defining climate feature. Swamps exist where water remains present for long periods and that persistent water continually evaporates into the air. Plants contribute additional moisture through transpiration, releasing water vapor during photosynthesis. The result is air that often holds a high concentration of moisture, particularly in warm seasons. High humidity directly affects the body's cooling system because sweat evaporates less efficiently when surrounding air is already saturated. Evaporation is essential for heat regulation. When sweat evaporates, it removes heat from the skin. In humid air, evaporation slows. Sweat accumulates rather than cooling effectively. This can create a misleading sensation. Someone may feel damp but not necessarily cooler. Over time, body temperature can rise steadily, increasing risk of heat exhaustion or heat-related illness, even when physical activity seems moderate. Airflow influences this process as well. Dense swamp vegetation often blocks wind, reducing convective cooling. Open landscapes allow breezes to carry away warm air near the skin. Under thick canopy, that air lingers. Combined with humidity, limited airflow creates a microclimate that traps heat close to the body. Solar exposure varies within swamps. Some areas have dense tree cover that diffuses sunlight. Others, especially marshy openings or mangrove edges, receive direct sun reflection from water surfaces. Reflected sunlight can increase perceived heat significantly. People moving between shaded forest patches and open water zones may underestimate how much energy those transitions demand. Ground conditions contribute indirectly to climate stress. Saturated soil conducts heat differently than dry ground. Standing water absorbs solar radiation during the day and releases heat slowly later. This thermal buffering stabilizes temperatures but often maintains warmth into evening hours, reducing nighttime cooling that might otherwise aid recovery from daytime exertion. Hydration challenges follow naturally. High humidity increases perspiration even during low-intensity activity. Wet clothing may conceal how much fluid loss has occurred. Thirst perception sometimes lags behind actual dehydration, particularly when attention focuses on navigation or environmental observation. Carrying treated drinking water becomes essential because surrounding water usually requires purification before safe consumption. Electrolyte balance also matters. Sweating removes not only water but also sodium and other minerals. Prolonged exposure without replenishment can lead to muscle cramps, fatigue, or dizziness. Outdoor professionals working in wetlands often incorporate electrolyte replacement strategies alongside water intake. Clothing choices influence heat management strongly. Lightweight, breathable fabrics help evaporation, but must also protect against insects, vegetation abrasion, and sun exposure. Waterproof materials protect against water contact, but can trap heat if ventilation is insufficient. Achieving balance requires experience with local conditions. Footwear deserves specific mention. Wet boots increase weight with each step. Prolonged dampness softens skin, increasing blister risk. Blisters combined with heat and humidity can become infected quickly. Proper sock selection, drying opportunities, and foot care routines significantly affect comfort and safety. Fatigue accumulates faster in swamp climates, partly because movement requires extra effort. Mud resistance, uneven terrain, and vegetation obstacles increase energy expenditure. When combined with heat stress, the body reaches fatigue thresholds sooner than expected. Rest intervals become important, even if progress feels slow. Heat exhaustion symptoms often begin subtly. Increased sweating, mild headache, irritability, or reduced concentration may precede more obvious signs like dizziness, nausea, or weakness. Recognizing early symptoms allows preventive actions such as resting in shade, hydrating, and cooling gradually. Heat stroke represents a more severe condition where body temperature regulation fails. Symptoms may include confusion, cessation of sweating despite heat, rapid pulse, or loss of consciousness. Immediate medical attention becomes critical. Fortunately, awareness and preparation greatly reduce likelihood. Seasonal variation affects swamp climate intensity. Tropical wetlands maintain high humidity year-round, while temperate swamps experience seasonal peaks. Summer months often present the greatest heat challenge. Planning activities during cooler parts of the day reduces risk. Acclimatization plays a role. People accustomed to humid climates often tolerate conditions better than newcomers. Physiological adaptation improves sweating efficiency and cardiovascular response over time. Gradual exposure helps the body adjust safely. Cloud cover influences thermal conditions. Overcast skies reduce direct solar radiation, but often accompany high humidity. The net effect may still feel warm because evaporative cooling remains limited. Clear sunny days increase radiant heat but sometimes coincide with lower humidity. Insect activity correlates with climate factors too. Warm, humid conditions favour mosquito breeding and activity. Additional insect presence increases discomfort, potentially distracting from hydration and heat monitoring. Integrated awareness helps maintain focus on overall safety. Nighttime conditions in swamps vary widely. Some areas cool moderately after sunset, while others retain warmth due to water heat storage. High nighttime humidity may interfere with sleep quality, affecting next-day energy levels for those camping or working in wetlands. Storm patterns influence climate challenges. Sudden rain increases humidity further and saturates clothing. Lightning risk rises in open wetland areas. After storms, standing water expands, altering terrain and insect populations simultaneously. Climate monitoring tools assist planning. Portable weather devices, smartphone forecasts and satellite data help anticipate temperature and humidity trends. Professional field teams often incorporate daily climate briefings into safety protocols. Environmental conservation intersects with climate considerations. Wetlands moderate regional temperatures by storing and releasing heat gradually. Loss of wetlands can intensify local climate extremes. Preserving swamps therefore supports broader climate stability. Psychological perception of heat differs from measured temperature. Humidity amplifies discomfort perception. Continuous mild discomfort can reduce morale, increasing fatigue indirectly. Recognizing this psychological component helps maintain realistic expectations. Medical preparedness includes recognizing personal limits. Individuals vary in heat tolerance based on fitness, hydration status, age, and medical conditions. Honest self-assessment prevents overexertion. Food intake influences heat resilience. Light, balanced meals support energy without increasing metabolic heat excessively. Heavy meals during peak heat can contribute to discomfort. Shade management becomes practical strategy. Resting under canopy, scheduling breaks near cooler water edges where airflow exists, and avoiding midday exposure improve endurance. Field researchers often establish base points where cooling measures are available, shaded rest areas, hydration supplies, first aid kits, and communication equipment. Structured planning reduces cumulative stress. Technological clothing advances include moisture-wicking fabrics, ventilated boots, and cooling accessories. These innovations improve comfort but still require careful use. Education programs for wetland visitors emphasize pacing. Slow, steady movement conserves energy better than alternating bursts of activity and rest. Consistent hydration complements pacing strategies. Long-term climate trends suggest some wetlands may experience increased heat stress due to global warming. Monitoring these trends helps update safety recommendations continuously. Despite challenges, many people work productively in swamp climates by adapting routines, equipment, and expectations. Knowledge transforms difficulty into manageable conditions rather than insurmountable obstacles. And while climate stress influences how the body responds physically, it also affects orientation and decision-making, especially in environments where visibility is limited and landmarks repeat, which naturally brings attention toward how navigation itself becomes complicated in swamp terrain, where getting lost can happen more easily than expected. If there is one challenge people consistently underestimate in swamp environments, it is navigation. From the outside, wetlands can look open enough to move through without much difficulty. Trees may appear spaced apart, water surfaces may look continuous, and the horizon often seems visible across low vegetation. Yet once inside, the terrain quickly reveals how disorienting it can become. Visual repetition, limited landmarks, water channels that shift over time, and constant environmental noise all combine to make orientation harder than many expect. One major factor is visual uniformity. In forests with varied elevation, rock formations, or clear trails, the eye picks up distinctive reference points easily. Swamps often lack those obvious markers. Similar tree species repeat across large areas. Water surfaces reflect surrounding vegetation, making distances difficult to judge. Floating plants create patterns that look alike in every direction. This visual consistency makes it easy to lose track of the path already travelled. Light conditions contribute to this effect. Dense canopy cover diffuses sunlight, reducing shadows that normally help define terrain contours. Reflected light from water surfaces further flattens visual contrast. Without clear shadow cues, estimating depth, distance and direction becomes more complicated. The environment may appear almost two-dimensional at times, especially during overcast weather. Sound perception changes as well. Vegetation absorbs some sounds while water reflects others unpredictably. Footsteps, animal calls, or distant human voices may seem closer or farther than they are. This acoustic distortion complicates orientation, particularly when people rely on sound to supplement visual navigation. Water movement patterns add another layer of complexity. Many swamps contain slow-flowing channels that change gradually with seasonal rainfall. What appears to be a consistent waterway may split, merge, or shift slightly from year to year. Maps can become outdated unless frequently updated. Even GPS data may not capture subtle hydrological changes affecting on-the-ground movement. Magnetic navigation sometimes encounters localized interference. Certain wetland soils contain minerals that affect compass readings slightly. While usually minor combined with other orientation challenges, these deviations can contribute to cumulative directional error over time. Experienced navigators cross-check compass readings with multiple environmental cues rather than relying on a single indicator. Footing considerations also influence navigation. People naturally adjust routes to avoid deep mud, dense vegetation, or unstable ground. These detours rarely follow straight lines. Over time, small deviations accumulate, resulting in unintended direction changes. Without conscious correction, travellers may gradually arc away from intended paths. Plant density can obscure distant landmarks completely. In some swamps, visibility may extend only a few meters in any direction. When every visible tree or shrub resembles the last, mental mapping becomes difficult. Even experienced field researchers sometimes mark routes physically, with temporary markers or digital waypoints. Water depth variation further complicates route planning. Shallow areas suitable for wading may border deeper pools requiring detours. Vegetation sometimes hides these transitions until encountered directly. Adjusting repeatedly to avoid deeper water alters travel direction incrementally. Fog formation occurs frequently over wetlands, particularly during early morning or evening when temperature differences between water and air create condensation. Fog reduces visibility dramatically. Orientation under fog conditions demands careful reliance on instruments and prior knowledge rather than visual cues alone. Seasonal flooding can transform familiar terrain. Trails disappear underwater. New channels form. Vegetation patterns shift. Someone returning to a previously visited wetland may find navigation assumptions no longer valid. Continuous observation rather than memory-based navigation becomes necessary. Technological navigation aids help but have limitations. GPS devices provide coordinates but may struggle under dense canopy cover. Battery life becomes critical during extended fieldwork. Waterproofing protects equipment but adds complexity. Redundancy, such as carrying both electronic and analog navigation tools, increases reliability. Digital mapping has improved wetland navigation significantly. Satellite imagery, LIDAR elevation data, and hydrological models offer detailed terrain understanding before entry. Still, real-time ground conditions may differ from remote observations due to seasonal or weather-related changes. Human cognitive factors play a role too. Fatigue from heat, humidity, insects, and physical exertion reduces concentration. Reduced concentration increases navigation error likelihood. Regular rest breaks help maintain situational awareness. Psychological stress also influences orientation. Environments perceived as unfamiliar or potentially risky can narrow attention focus. Tunnel vision reduces awareness of broader spatial context. Calm, deliberate movement supports better orientation than rush travel. Training improves navigation outcomes substantially. Field researchers learn to interpret subtle cues such as vegetation type changes, indicating elevation differences, watercolor variations suggesting depth shifts, or bird flight patterns hinting at open water nearby. These observational skills supplement instrument-based navigation. Local knowledge remains invaluable. Communities living near wetlands often develop intuitive understanding of seasonal patterns, safe routes, and environmental signals. Collaboration between local residents and visiting researchers enhances navigation safety. Emergency preparedness includes planning for disorientation scenarios. Carrying signalling devices, communication tools, and sufficient supplies allows safe response if navigation errors occur. Search and rescue teams prioritize wetlands as areas requiring specialized planning due to terrain complexity. Infrastructure solutions sometimes assist navigation. Boardwalks, marked trails, observation towers, and signage provide structured routes in protected wetlands. These features reduce environmental impact while improving visitor safety. Night navigation introduces additional challenges. Reduced visibility, increased insect activity, and altered animal behavior complicate movement. Unless necessary, nighttime wetland travel is generally avoided or conducted with specialized equipment. Hydrological monitoring helps predict navigation difficulty. Water level gauges, rainfall data, and seasonal forecasts inform access planning. Field teams often schedule activities during lower water periods when possible. Environmental conservation considerations influence navigation practices. Minimizing disturbance to fragile vegetation, avoiding wildlife nesting areas, and preventing soil compaction protect ecosystem health while ensuring safe passage. Communication planning is critical. Cellular coverage may be unreliable in remote wetlands. Satellite communication devices or radio systems provide alternatives. Prearranged check-in schedules enhance safety. Education programs for recreational visitors emphasize staying on marked paths when available. Unstructured exploration increases both personal risk and ecological disturbance. Responsible tourism balances curiosity with caution. Historical exploration accounts frequently highlight navigation difficulties in wetlands. Early expeditions documented slow progress, repeated disorientation, and reliance on indigenous guides familiar with terrain. These accounts illustrate long-standing recognition of swamp navigation complexity. Climate change may alter wetland navigation patterns over time. Rising water levels, vegetation shifts, and increased storm frequency affect terrain accessibility. Continuous monitoring informs updated guidance. Personal navigation habits make a difference. Regularly checking direction, marking progress mentally or digitally, and maintaining awareness of entry points reduce likelihood of becoming lost. Complacency often contributes more to disorientation than environmental hostility. Ultimately, swamp navigation challenges stem from a combination of environmental structure, climate, biological activity, and human perception. Understanding these factors allows preparation rather than surprise. The environment remains complex but manageable with knowledge, and as navigation difficulty often intersects with water hazards that are not always obvious from the surface, it becomes important to look more closely at how seemingly shallow wetlands can still pose drowning risks even where deep open water is not immediately visible, which leads naturally toward examining how bogs, soft sediment and hidden pools create unexpected water safety challenges. When people think about drowning, the usual image involves deep lakes, fast rivers, or open ocean water. Depth seems like the obvious risk factor. In swamp environments, however, danger sometimes appears in places that do not look deep at all. Shallow-looking bogs, soft sediment, floating vegetation mats, and slow-moving water channels can create conditions where mobility becomes restricted, balance is compromised, and self-rescue becomes more difficult than expected. It is rarely a dramatic scenario. More often, it develops gradually through fatigue, disorientation, or unstable footing. Bogs represent a specific type of wetland within the broader swamp landscape, though the terms are sometimes used interchangeably in casual conversation. True bogs form in areas where water accumulates faster than it drains, often fed mainly by rainfall rather than groundwater or streams. The result is acidic, nutrient-poor water and thick peat accumulation. That peat layer can look solid but behaves more like a saturated sponge. When weight is applied, it compresses unevenly and may release trapped water upward. This compression effect contributes to instability. A person stepping onto peat may sink slowly, not dramatically, but enough to alter balance. If both feet sink unevenly, movement becomes awkward. Removing a foot requires effort because suction develops as water fills the void left behind. That repeated resistance increases fatigue quickly, especially in warm, humid conditions already stressing the body. Floating vegetation mats add another dimension. Mosses, grasses and other plants sometimes form interconnected layers that float partially on underlying water. From above they resemble continuous ground. Under pressure they flex. Some areas support weight briefly, others collapse partially. The unpredictability requires careful probing before stepping, a practice common among experienced wetland researchers. Water channels hidden beneath vegetation present additional risk. Slow-moving water erodes pathways under plant cover. Surface vegetation remains intact while water depth increases underneath. Someone walking across such a surface may suddenly encounter deeper water without visual warning. Balance loss in these situations can lead to falls that complicate recovery. Clothing and equipment influence outcomes significantly. Heavy boots filled with water increase weight. Backpacks absorb moisture. Wet clothing restricts movement. These factors make climbing out of soft sediment or shallow water more physically demanding. Preparation with waterproof or quick dry gear helps mitigate this effect. Fatigue remains a central contributor. Moving through swamp terrain requires constant attention to footing, navigation, insects, and temperature regulation. When exhaustion sets in, balance control decreases, small slips become more likely. Recovery from slips requires energy that may already be limited. Water temperature also matters. Even in warm climates, prolonged immersion can reduce body temperature gradually. Wet clothing conducts heat away from the body. Combined with fatigue, this can impair coordination. In cooler climates, hypothermia becomes a realistic risk even in shallow water if exposure lasts long enough. Visibility challenges amplify the problem. Tannin-stained water, common in peat-rich wetlands, obscures depth perception. Reflections from sky or vegetation further reduce clarity. Depth estimation becomes guesswork rather than observation. Without probing tools, stepping decisions rely on incomplete information. Gas bubbles produced by anaerobic decomposition sometimes accumulate within peat layers. When disturbed, they release, altering soil consistency suddenly. While usually harmless chemically in open environments, their release can reduce surface stability temporarily. Water flow, though often slow, still exerts influence. Slight currents near channels or drainage points can destabilize footing. Combined with soft sediment, even gentle flow increases effort needed to maintain balance. Plant roots complicate extraction from soft ground. Root networks stabilize peat, but also create irregular resistance patterns. A foot caught between roots may require careful repositioning rather than simple lifting. Seasonal variation affects bog stability significantly. Wet seasons raise water tables, softening surfaces further. Dry periods may firm surfaces slightly, but do not eliminate underlying saturation. Freeze-thaw cycles in colder regions alter peat structure over time. Human modification sometimes worsens conditions. Drainage attempts leave uneven sediment. Abandoned infrastructure creates hidden hazards. Disturbed vegetation mats may appear stable but lack original root integrity. Historical accounts of wetland travel often mention slow progress through bogs rather than sudden accidents. Travellers described exhaustion, equipment loss, and gradual sinking rather than dramatic immersion. These narratives align with modern field experience. Search and rescue operations treat bog environments cautiously. Rescuers use boards, ropes, or flotation aids to distribute weight. Direct approach without support risks additional entrapment. Educational programs emphasize testing ground before committing full weight. Poles, sticks, or trekking staffs provide valuable feedback about firmness and depth. This simple technique prevents many incidents. Navigation planning includes avoiding known bog zones when possible. Topographic maps, satellite imagery, and local knowledge help identify high-risk areas. Elevated ridges often provide safer passage. Hydration management intersects with bog safety. Fatigue from dehydration reduces coordination. Carrying treated water and maintaining electrolyte balance supports physical stability. Communication preparedness matters. Remote wetlands often lack reliable cellular coverage. Satellite communication devices improve emergency response capability. Wildlife movement patterns sometimes indicate safer routes. Larger animals tend to follow firmer ground. Observing tracks can provide clues, though reliance solely on animal trails requires caution. Clothing maintenance helps prevent complications. Regularly removing mud buildup from boots reduces additional weight. Keeping spare dry clothing improves thermal regulation. Environmental conservation considerations intersect with safety. Excessive foot traffic damages vegetation mats, increasing erosion and instability. Staying on established paths when available protects both ecosystem and traveller. Scientific research continues exploring peat soil mechanics. Understanding compression behaviour, water retention, and gas dynamics informs infrastructure design and safety guidelines. Climate change influences bog conditions. Altered rainfall patterns, temperature shifts, and vegetation changes affect peat stability over time. Monitoring programs track these trends. Public perception sometimes exaggerates dramatic bog hazards, while overlooking cumulative fatigue and navigation factors that contribute more frequently to incidents. Balanced education improves preparedness. Technological tools like ground-penetrating radar help researchers assess peat depth and water channels. These tools enhance understanding but are not practical for everyday visitors. First aid knowledge supports response to minor immersion incidents. Treating cuts promptly, warming the body gradually, and rehydrating reduce complication risk. Ultimately, drowning risk in swamp environments rarely stems from obvious deep water. Instead, it emerges from a combination of soft ground, hidden channels, fatigue, equipment weight, and environmental conditions. Awareness transforms these factors from surprises into manageable challenges. And as physical hazards connect closely with human history and wetlands, it becomes useful to consider how past explorers, settlers, and local communities interacted with swamp environments, because historical encounters often reveal patterns of adaptation, misunderstanding, and survival that continue shaping how these ecosystems are approached today. Human interaction with swamp environments stretches back as far as recorded history and probably much further. Wherever wetlands existed, people found ways to live near them, travel through them, extract resources from them, or avoid them altogether depending on local conditions. These encounters rarely produce simple stories. Swamps have offered food, shelter, and strategic protection. At the same time, they presented disease risk, navigation challenges, and environmental obstacles. Looking at historical experiences helps explain why wetlands still carry such a strong reputation today, not because they were always hostile, but because they required adaptation and respect from anyone entering them. Early agricultural societies often settled near wetlands despite the challenges. Floodplains and swamps provided fertile soil, enriched by periodic sediment deposits. Ancient river civilizations in places like Mesopotamia, the Nile Delta, and parts of Southeast Asia relied heavily on wetland ecosystems for food production. Rice cultivation in particular developed alongside swampy conditions, using controlled flooding to support crops. These communities learned water management techniques, built raised living areas, and developed seasonal rhythms aligned with wetland cycles. At the same time, wetlands influence public health historically. Before modern medicine, mosquito-borne diseases like malaria shaped settlement decisions. Certain regions remained sparsely populated, not because they lacked resources, but because disease risk made permanent habitation difficult. Historical records from Europe, Africa, Asia, and the Americas all mention wetlands in connection with seasonal illness patterns. Over time, some societies drained swamps intentionally to reduce disease prevalence, sometimes improving public health while simultaneously altering ecosystems. Travel through wetlands historically required specialized knowledge. Indigenous communities often developed sophisticated navigation skills based on vegetation patterns, water flow cues, bird behavior, and seasonal markers. These knowledge systems rarely appeared in written records initially, but proved essential to explorers, traders, and settlers who lacked local familiarity. Many historical expeditions depended on local guides who understood safe routes through otherwise confusing terrain. Military history also intersects with swamp environments. Wetlands sometimes provided natural defensive barriers. Armies unfamiliar with local terrain struggled with mobility, supply logistics, and disease exposure. Historical battles in swamp regions frequently highlight how terrain itself influenced outcomes. In some cases, local populations used wetlands strategically to resist invasion, knowing that adversaries would face navigation and health challenges. Maritime trade routes occasionally passed near coastal swamps, particularly mangrove forests. These environments provided sheltered anchorages but also required careful navigation to avoid shallow channels and submerged routes. Historical shipping logs include numerous references to vessels grounding in mangrove-lined waters, demonstrating how even experienced sailors needed caution. Colonial expansion periods produced many written accounts of swamp encounters. Explorers documented dense vegetation, insect populations, unfamiliar wildlife, and navigation difficulty. Some reports exaggerated dangers, reflecting cultural bias or limited ecological understanding. Others offered careful observation that later informed scientific study. These narratives shaped public perception for generations. Economic use of wetlands has a long history as well. Timber harvesting in swamp forests supplied building materials. Fishing communities relied on wetland nurseries where fish populations thrived. Fur trapping in North American wetlands supported trade networks for centuries. These activities required adaptation to wetland conditions rather than avoidance. Infrastructure development presented persistent challenges. Building roads, railways, or settlements on saturated ground required engineering innovation. Early attempts sometimes failed due to soil instability. Over time, techniques such as elevated causeways, drainage channels, and reinforced foundations improved success rates. These engineering solutions still influence modern wetland infrastructure. Cultural stories about swamps often blend practical experience with symbolism. Folklore from many regions portrays wetlands as mysterious or unpredictable places. These narratives sometimes served educational purposes, discouraging children or inexperienced travellers from entering hazardous terrain without preparation. Oral traditions preserved practical safety knowledge in memorable forms. Scientific exploration of wetlands increased during the 19th and 20th centuries. Naturalists began documenting biodiversity, hydrology, and ecological processes systematically. Their work gradually shifted perception from purely dangerous landscapes to valuable ecosystems. Conservation movements later built on this scientific understanding. Historical medical practices also intersected with wetland environments. Before germ theory, people attributed swamp-related illness to bad air or miasma. While scientifically inaccurate, this observation indirectly recognized that certain environments correlated with disease. Later understanding of mosquitoes as disease vectors clarified the mechanism. Archaeological discoveries in wetlands reveal another dimension. Waterlogged conditions sometimes preserve organic materials that decay elsewhere. Ancient wooden structures, textiles, food remnants, and even human remains have been recovered from peat bogs. These finds provide valuable insight into past cultures and environmental conditions. Wetlands also offered refuge historically. Escaped enslaved people in parts of the Americas formed communities in remote swamps where pursuit was difficult. These communities developed unique cultural identities shaped partly by environmental adaptation. Similar refuge use appears in other historical contexts worldwide. Literature and art frequently reflect historical swamp encounters. Travel journals, novels, and paintings often depict wetlands as both beautiful and challenging. These artistic interpretations influenced public imagination as much as scientific reports did. Modern conservation efforts often draw on historical land use records. Understanding how wetlands changed over time helps guide restoration projects. Historical maps, photographs, and written descriptions inform ecological baselines. Technological advances have transformed wetland interaction. Motorized boats, satellite navigation, insect repellents, and modern medicine reduce many risks that historically limited human presence. Yet environmental conditions themselves remain largely unchanged. Educational programs increasingly incorporate historical context when teaching about wetlands. Linking past experiences with present ecological understanding helps build comprehensive awareness. History provides perspective on how perceptions evolved. Climate records extracted from peat layers offer historical environmental data. Scientists analyze preserved pollen, charcoal, and chemical signatures to reconstruct past climate patterns. Wetlands thus serve as natural archives of environmental history. Cultural heritage preservation sometimes focuses on wetland communities whose traditions revolve around fishing, agriculture, or craft production tied to swamp ecosystems. Maintaining these traditions requires balancing conservation with sustainable use. Tourism in historic wetland areas often combines ecological and cultural interpretation. Guided visits may highlight both natural features and historical human interaction. This integrated approach enhances public understanding. Disaster history includes wetland-related events as well. Flooding patterns influence settlement design. Some communities relocated repeatedly due to changing water levels. Historical resilience strategies inform modern climate adaptation planning. International environmental policy increasingly recognizes wetlands' historical importance alongside ecological value. Agreements like the Ramsar Convention promote wetland conservation globally, partly acknowledging past overexploitation. Public perception continues evolving. Swamps once viewed primarily as obstacles now attract scientific interest, conservation investment, and educational tourism. Historical experience contributes to that shift. Ultimately, human stories from swamps reveal adaptation rather than simple conflict. Communities learn to live with wetland conditions, extracting benefits while managing risks. Understanding these historical encounters provides context for current safety practices and conservation priorities. And as history shows how humans interacted with wetlands during everyday life and settlement, it also reveals how swamps played roles during conflict situations, where terrain influenced military movement, survival strategies, and tactical decisions, which naturally leads toward examining how swamp environments intersected with warfare and survival scenarios across different periods. Wetlands have influenced conflict and survival situations for as long as organised human movement across landscapes has existed. Swamps rarely appear as the central objective in warfare, yet they frequently shape how conflicts unfold. Terrain influences mobility, supply routes, visibility, health conditions, and defensive strategy. When armies, refugees, explorers, or displaced communities move through swamp environments, the same environmental factors already discussed — unstable ground, dense vegetation, humidity, disease vectors, and navigation difficulty — begin to interact with stress, urgency, and limited resources. That combination historically made wetlands both protective refuges and serious logistical challenges. One of the most straightforward military impacts of swamps involves mobility. armies traditionally depend on predictable movement of personnel, equipment, and supplies. Saturated soils slow vehicles, animals, and foot soldiers alike. Heavy equipment bogs down easily. Artillery placement becomes difficult on unstable ground. Even basic marching speed drops significantly compared with dry terrain. Historical campaign records repeatedly note delayed troop movements when swamp crossings became unavoidable. Defensive advantages arise naturally from those mobility constraints. Communities familiar with local wetlands sometimes use swamps as buffers against invading forces. Dense vegetation limits visibility. Narrow, firm pathways become choke points. Knowledge of seasonal water levels allows defenders to anticipate where movement remains possible. This terrain familiarity often compensates for smaller force size. Such strategies appear in historical accounts from many regions, including Southeast Asia, parts of Africa, Eastern Europe, and the Americas. Disease exposure historically represented one of the most significant wartime swamp hazards. Before modern medical understanding and mosquito control, armies operating in wetland regions often experienced high illness rates. Malaria, dysentery, and other water or insect-related diseases weakened forces sometimes more than combat itself. Military medical logs from multiple centuries describe reduced operational readiness linked directly to wetland exposure. Supply logistics in swamp environments require adaptation. Traditional wagons or pack animals struggle in saturated soil. Water transport sometimes becomes preferable, but waterways may be shallow, obstructed, or unfamiliar. Establishing reliable supply lines through wetlands often demands engineering solutions such as temporary bridges, corduroy roads built from logs, or elevated walkways. These structures require labour, time, and materials that may not always be available. Camouflage opportunities also exist. Dense vegetation provides concealment for both defensive positions and movement. Guerrilla warfare tactics frequently exploit wetland terrain. Small groups familiar with local geography can move quietly, establish temporary camps, and avoid detection. This pattern appears in multiple historical contexts, where local fighters used environmental knowledge strategically. Survival situations unrelated to warfare show similar patterns. Explorers, lost travellers, or displaced populations sometimes turn to wetlands for refuge because these environments offered water, food sources, and concealment. Fishing, trapping, and foraging in wetlands can sustain communities when other resources are scarce. However, survival requires knowledge of safe water treatment, edible plants, wildlife behaviour, and navigation. Food availability in swamps varies widely but often includes fish, amphibians, birds, small mammals, and certain edible plants. Historical survival accounts frequently mention reliance on such resources. Preparation methods become critical because improper handling increases disease risk. Traditional ecological knowledge often guided safe practices. Water availability, while abundant, presents treatment challenges. Standing water frequently contains microorganisms unsuitable for direct consumption. Historical survival strategies included boiling, filtering through cloth, or selecting flowing water channels when available. Modern purification technologies improve safety but require planning. Shelter construction in wetlands demands attention to ground stability. Raised platforms, tree-supported structures, or floating arrangements help avoid prolonged contact with saturated soil. Indigenous architectural traditions in many wetland regions reflect centuries of adaptation to these conditions. Fire management presents additional complexity. Damp fuel sources make ignition difficult. Elevated platforms or specially prepared fire bases sometimes become necessary. Smoke management matters too because visibility affects both safety and concealment depending on context. Psychological factors influence survival outcomes significantly. Wetland environments often produce sensory overload. Constant insect noise, humidity discomfort, reduced visibility, and unfamiliar wildlife sounds. Stress management becomes important for maintaining clear decision-making. Historical survival narratives frequently emphasize maintaining routine and morale under challenging conditions. Weather variability compounds difficulty. Sudden storms raise water levels quickly. Wind shifts alter travel routes. Temperature fluctuations affect both physical endurance and equipment performance. Survival planning must incorporate flexibility. Modern military training often includes wetland survival modules precisely because of these challenges. Personnel learn navigation, water purification, insect protection, and equipment maintenance specific to humid environments. Such training reflects lessons learned historically. Environmental ethics considerations increasingly influence modern military operations. Wetlands provide critical ecological services, so minimizing long-term environmental damage has become part of operational planning in many contexts. Search and rescue operations in swamp terrain draw on similar survival principles. Teams prepare for slow movement, high humidity, limited visibility, and communication challenges. Specialized vehicles, boats, or aerial support often assist. Technological advancements have improved outcomes in wetland operations. Satellite imagery, GPS navigation, lightweight water purification systems, and improved protective clothing reduce some historical difficulties. Nevertheless, environmental conditions themselves remain largely unchanged. Cultural narratives about wartime swamp experiences often highlight resilience and adaptation. Memoirs, oral histories, and literature document how individuals coped with terrain challenges alongside human conflict. These accounts contribute to broader understanding of environmental influence on history. Economic consequences sometimes follow wartime wetland use. Infrastructure built for military purposes occasionally transitions to civilian use afterward. Conversely, environmental damage may require restoration efforts. Wetlands as refuge extend beyond warfare. Natural disasters, political upheaval, or social displacement have driven communities into remote swamp regions historically. Such communities often develop sustainable practices suited to wetland living over time. Scientific research into wetland survival strategies includes anthropology, ecology, and environmental history. Interdisciplinary study reveals how human adaptation intersects with ecosystem function. Public education increasingly incorporates these historical perspectives when discussing wetlands. Understanding past challenges helps contextualize present conservation and safety practices. Emergency preparedness agencies sometimes use historical case studies to inform planning. Lessons learned from past wetland operations improve future response effectiveness. Climate change may alter the strategic importance of wetlands. Rising sea levels, shifting precipitation patterns, and habitat changes influence accessibility and ecological dynamics. Ultimately, swamps in warfare and survival contexts illustrate how environmental factors shape human experience beyond immediate ecological interaction. Terrain, climate, biology, and psychology intersect to influence outcomes. And as historical and survival perspectives show how humans struggle in these environments, while many animals thrive, it becomes useful to examine why wildlife often adapts so successfully to swamp conditions that challenge people, which naturally leads toward understanding the biological advantages animals possess in wetland ecosystems. One of the most noticeable contrasts in swamp environments is how comfortable wildlife often appears compared with how challenging the same terrain feels for humans. Animals move through dense vegetation, shallow water, mud, and humidity with apparent ease. Birds land precisely on narrow branches. Amphibians navigate submerged terrain effortlessly. Reptiles glide through murky water, where human footing feels uncertain. This contrast does not reflect hostility from the environment toward people. It reflects evolutionary specialization. Animals that live in wetlands possess anatomical, physiological, and behavioral adaptations shaped over thousands or millions of years, while humans usually enter these environments only occasionally. mobility provides the most obvious example. Many swamp animals have physical structures specifically suited for saturated terrain. Wading birds such as herons or storks possess long legs that keep their bodies above water while allowing slow, deliberate movement through shallow pools. Their toes spread weight across soft sediment, reducing sinking. Mammals like swamp deer or moose show similar principles, with broad hooves that distribute weight effectively over mud. Reptiles demonstrate another mobility strategy. Crocodilians, turtles, and certain snakes have bodies adapted for both aquatic and terrestrial movement. Streamlined shapes reduce resistance in water. Muscular tails assist propulsion. Scales protect skin from prolonged moisture exposure. These adaptations allow seamless transition between water and land that humans, with upright posture and limited skin protection, find much more difficult. Amphibians represent perhaps the most specialized wetland residents. Frogs, salamanders, and similar species rely on moisture for skin respiration or reproduction. Their permeable skin allows gas exchange directly with water, something humans cannot do. This biological difference alone explains why amphibians feel at home in environments that would cause human skin irritation or infection over extended exposure. Thermoregulation offers another advantage. Many swamp animals are ectothermic, meaning their body temperature depends partly on environmental conditions. Reptiles bask when warmth is needed and retreat to water or shade to cool. This flexibility reduces metabolic stress. Humans maintain constant internal temperature through metabolic energy, which becomes more difficult in humid heat where cooling efficiency decreases. Water balance adaptation matters too. Animals native to wetlands often possess efficient kidney function suited to variable hydration conditions. Some can tolerate brackish or fluctuating salinity environments. Humans require treated fresh water consistently, and dehydration risk increases quickly in humid climates where sweating remains constant. Sensory adaptation significantly influences comfort. Many wetland animals rely less on vision alone. Birds detect subtle water ripples indicating prey movement. Fish sense vibrations through lateral line systems. Mammals use smell extensively. Humans depend heavily on vision, yet swamp environments often reduce visibility through vegetation density, water turbidity, and diffused lighting. Camouflage provides safety and hunting efficiency for animals. Colour patterns blending with mud, leaves, or water reflections help predators approach prey, and prey avoid predators. Humans lack natural camouflage in most wetlands, and rely on clothing or equipment to compensate. Behavioural adaptation also plays a role. Animals active in wetlands often adjust activity timing to environmental conditions. Nocturnal feeding avoids daytime heat. Seasonal migration tracks water availability. Humans tend to maintain fixed schedules, sometimes ignoring environmental rhythms that wildlife follows naturally. Dietary flexibility helps many species thrive. Fish feed on aquatic insects, plants, or smaller fish. Birds exploit diverse food sources depending on availability. Mammals adapt feeding patterns seasonally. Humans entering wetlands depend on carried supplies unless trained in local foraging knowledge. Reproductive strategies further illustrate adaptation. Amphibians lay eggs in water where larvae develop safely. Many fish species spawn in wetlands because shallow water provides protection from larger predators. Birds build nests elevated above water or within dense vegetation. These strategies maximize offspring survival in saturated environments. Disease resistance represents another adaptation. Animals native to wetlands often coexist with parasites or pathogens without severe symptoms. Their immune systems evolved alongside local microorganisms. Humans lacking such evolutionary exposure may experience stronger reactions. Foot structure offers a practical advantage. Webbed feet in birds, amphibians, and some mammals improve swimming efficiency and stability on soft surfaces. Humans require footwear modifications to approximate similar functionality. Energy expenditure efficiency differs too. Animals evolved movement patterns minimizing effort in their native terrain. Humans unfamiliar with swamp locomotion expend extra energy maintaining balance, extracting feet from mud, and navigating obstacles. Communication systems also adapt to wetland acoustics. Frogs use calls that carry effectively over water. Birds adjust vocal frequencies suited to vegetation density. Humans may find communication difficult due to sound absorption and reflection patterns. Shelter adaptation highlights further differences. Many animals construct nests, burrows, or resting sites suited to moisture conditions. Beavers build lodges above water level. Birds select branches unlikely to flood. Humans require artificial shelter construction or protective equipment. Predator-prey dynamics in wetlands reflect evolutionary balance. Species evolved awareness of local predator cues. Humans entering unfamiliar ecosystems may misinterpret or overlook such signals. Longevity in wetland environments often correlates with specialization. Species that cannot tolerate saturated conditions simply do not persist there. This ecological filtering results in communities composed primarily of adapted organisms. Microbial symbiosis sometimes benefits animals. Gut microbiomes assist digestion of wetland vegetation. Skin microbiota may protect against pathogens. Research continues exploring these relationships. Technological innovation helps humans compensate. Waterproof clothing, insect repellents, navigation tools, and water purification systems extend human capability. Still, these remain external aids rather than inherent adaptations. Cultural adaptation provides another layer. Indigenous communities living near wetlands develop traditional ecological knowledge covering navigation, food sources, seasonal patterns, and safety practices. This knowledge represents accumulated human adaptation over generations. Conservation efforts recognize that wetland biodiversity depends on these specialized adaptations. Protecting habitat preserves evolutionary relationships that allow species to thrive. Climate change may challenge even well-adapted species. Altered water levels, temperature shifts, and habitat fragmentation affect wetland wildlife. Monitoring these impacts remains an active research area. Human recreation in wetlands increasingly emphasizes observation rather than intrusion. Boardwalks, guided tours, and remote sensing allow appreciation without disrupting adapted species. Education about wildlife adaptation fosters respect. Understanding why animals thrive reduces unrealistic expectations about human performance in the same environment. Public safety messaging often frames adaptation positively. Rather than portraying wetlands as hostile, it highlights preparation and learning from wildlife behavior. Scientific study of wetland adaptation contributes to broader biological understanding. Insights into respiration, osmoregulation, and locomotion have applications beyond ecology. Ultimately, animals thrive in swamps because their bodies, behaviors, and life cycles evolved in direct response to those conditions. Humans can visit successfully with knowledge and preparation, but inherent adaptation differences remain. And recognizing how animals flourish in environments that challenge humans naturally leads toward considering the ecological importance of these wetlands themselves, because the very conditions that make them difficult for people often allow them to perform vital environmental functions on a global scale. When people focus on the difficulties of swamp environments, unstable ground, humidity, insects, navigation challenges, or wildlife encounters, it is easy to overlook the reason these ecosystems exist in the first place. Swamps are not accidental wastelands. They perform essential ecological functions that support biodiversity, regulate climate, protect coastlines, and maintain water quality on a scale that extends far beyond their boundaries. The same characteristics that make them demanding for human travel often allow them to operate as highly productive and stabilizing parts of the global environment. One of the most significant roles wetlands play involves water regulation. Swamps act like natural sponges. During heavy rainfall or seasonal flooding, they absorb excess water, slowing its movement across landscapes. Instead of rapid runoff, overwhelming rivers and urban drainage systems, wetlands distribute water gradually. This buffering effect reduces downstream flooding risk. Cities located near preserved wetlands often experience less severe flood damage compared with areas where wetlands have been drained. The mechanism behind this buffering is straightforward but powerful. Vegetation slows water flow. Saturated soil absorbs additional moisture until reaching capacity. Root systems stabilize sediment, preventing erosion that would otherwise increase water turbidity. Over time, this steady moderation shapes entire watershed dynamics. Removing wetlands frequently results in increased flood frequency and severity, a pattern documented in multiple regions globally. Water purification represents another crucial function. As water moves through swamp vegetation and soil, physical, chemical, and biological processes filter pollutants. Sediment settles out. Nutrients like nitrogen and phosphorus are absorbed by plants or transformed by microorganisms. Some contaminants break down through microbial metabolism. The resulting water often emerges cleaner than when it entered. Municipal water treatment systems sometimes rely indirectly on upstream wetlands for this natural filtration service. Carbon storage forms a major component of wetland ecological importance. Waterlogged conditions slow decomposition, allowing organic material to accumulate as peat or sediment. This process traps carbon that might otherwise enter the atmosphere as carbon dioxide. Wetlands therefore function as carbon sinks. Disturbing these ecosystems through drainage or development can release stored carbon, contributing to climate change. Conservation efforts increasingly emphasize wetland preservation partly for this reason. Biodiversity support is another defining feature. Swamps provide habitat for fish, amphibians, reptiles, birds, mammals, insects, and plants adapted to saturated conditions. Many species depend specifically on wetlands for breeding or feeding. Fish nurseries often occur in shallow wetland waters where young fish find protection from predators. Migratory birds use wetlands as rest stops during long journeys. Amphibians require aquatic environments for egg development. Removing wetlands disrupts these life cycles. Food web complexity in swamps often exceeds that of nearby dry ecosystems. Abundant plant growth supports herbivores. Those herbivores support predators. Microbial communities recycle nutrients continuously. This interconnected system contributes to overall ecosystem resilience. Loss of wetlands can cascade through food chains, affecting species far beyond the immediate area. Coastal swamps, including mangrove forests, provide shoreline protection. Dense root networks dissipate wave energy from storms and tidal surges. These natural barriers reduce erosion and protect inland communities. Regions with intact mangrove swamps often experience less severe storm damage than areas where mangroves have been removed. Climate regulation extends beyond carbon storage. Wetlands influence local temperature patterns through evapotranspiration. Water evaporation and plant transpiration release moisture into the atmosphere, moderating temperature extremes. This effect can reduce heat intensity locally and influence regional weather patterns. Soil formation processes in wetlands contribute to long-term landscape evolution. Accumulating organic matter gradually builds elevation in some areas. Sediment trapping alters river channels over time. These processes operate slowly but significantly. Economic value also emerges from ecological function. Fisheries supported by wetland nurseries sustain commercial and subsistence fishing industries. Timber harvested sustainably from swamp forests provides building materials. Ecotourism centered on wetland biodiversity generates income while encouraging conservation. Medicinal research increasingly recognizes wetland biodiversity as a source of pharmaceutical compounds. Plants, fungi, and microorganisms adapted to saturated environments produce unique chemicals. Some of these compounds have medical applications, and ongoing research continues exploring this potential. Cultural importance accompanies ecological value. Many communities maintain traditions tied to wetlands, including fishing practices, craft production, and spiritual associations. Preserving wetlands helps preserve cultural heritage as well. Hydrological connectivity between wetlands and surrounding ecosystems influences nutrient cycling. Wetlands intercept agricultural runoff, reducing nutrient overload in rivers and coastal waters. This function helps prevent harmful algal blooms and maintains aquatic ecosystem health. Wildfire mitigation represents another benefit in some regions. Saturated soils resist ignition, acting as fire breaks. During drought conditions, wetlands may still provide relative moisture compared with surrounding landscapes. Scientific research in wetlands contributes to understanding global environmental processes. Climate scientists study peat layers for historical climate records. Biologists investigate adaptation mechanisms. Hydrologists analyze water cycle interactions. These studies inform broader environmental management strategies. Restoration ecology increasingly focuses on wetland recovery, where drainage or development previously occurred. Re-establishing natural water flow, vegetation and soil structure can restore ecological function. Such projects often improve biodiversity and reduce flood risks simultaneously. Urban planning now sometimes integrates constructed wetlands for stormwater management. These engineered systems mimic natural swamp functions, filtering pollutants and moderating runoff. While not identical to natural wetlands, they demonstrate recognition of ecological services. Public perception has shifted gradually. Swamps, once considered obstacles or unhealthy environments, are now often valued for conservation. Educational outreach emphasizes ecosystem services alongside safety considerations. Policy frameworks at national and international levels support wetland protection. Agreements such as the Ramsar Convention encourage sustainable management. Local regulations often restrict wetland development to preserve ecological function. Climate change adds urgency to wetland conservation. Rising sea levels threaten coastal swamps. Altered precipitation patterns affect freshwater wetlands. Protecting and restoring wetlands contributes to climate adaptation strategies. Technological monitoring aids conservation. Satellite imagery tracks wetland extent changes. Environmental sensors measure water quality. Data-driven management improves effectiveness. Community involvement strengthens conservation outcomes. Local stewardship programs, citizen science initiatives, and educational partnerships foster engagement. Balancing human use with ecological preservation remains complex. Agriculture, urban expansion, and resource extraction sometimes conflict with conservation goals. Integrated planning seeks compromise solutions. Ultimately, swamps matter not despite their challenges but partly because of them. Conditions difficult for humans often create niches supporting biodiversity, water regulation, and climate stabilization. Recognizing ecological importance encourages respectful interaction rather than avoidance. And as environmental conditions shift globally, the stability of wetland ecosystems themselves becomes a subject of increasing concern, particularly as climate change influences water levels, temperature patterns, and species distribution, which leads naturally toward examining how evolving climate conditions may alter both the benefits and risks associated with swamp environments. Wetlands have always changed over time. Seasonal flooding, drought cycles, sediment deposition, and vegetation shifts are part of their natural rhythm. What has begun to change more noticeably in recent decades is the pace and scale of those changes. Climate patterns influence rainfall intensity, temperature averages, storm frequency, and sea levels, all of which directly affect swamp ecosystems. These environmental shifts do not simply alter scenery, they reshape hydrology, wildlife distribution, disease ecology, human settlement safety, and the practical risks associated with moving through or living near wetlands. Temperature increases are among the most widely observed climate trends. Warmer air holds more moisture, which influences precipitation patterns and humidity levels. In wetland environments, higher temperatures often extend growing seasons for vegetation and increase microbial activity. Faster decomposition changes soil chemistry. At the same time, increased evaporation may lower water levels in some regions, while intensified rainfall raises them elsewhere. These seemingly contradictory effects depend heavily on local geography. Sea level rise presents a particular concern for coastal swamps, especially mangrove ecosystems. Saltwater intrusion moves inland as sea levels climb. Freshwater vegetation may struggle under increased salinity, leading to species turnover. Some wetlands migrate inland naturally if space allows, but urban development often blocks that movement. When migration pathways are restricted, wetland loss can accelerate, reducing natural coastal protection against storms. Storm intensity changes also affect wetlands. Stronger storms bring heavier rainfall, storm surges, and altered sediment distribution. Flooding may expand temporarily or permanently. Vegetation damage alters habitat structure. Infrastructure near wetlands faces increased flood risk when natural buffering capacity becomes overwhelmed. Communities historically protected by wetlands may experience changing risk levels. Drought cycles influence wetlands in different ways. Reduced rainfall lowers water tables, exposing peat soils to air. Once oxygen reaches previously saturated organic layers, decomposition accelerates, releasing stored carbon. This process contributes to greenhouse gas emissions, creating feedback loops that further influence climate. Exposed peat can also become susceptible to fire under prolonged dry conditions. Vegetation shifts accompany climate change. Some plant species expand their range as temperatures rise while others retreat. Invasive species may gain advantage under altered conditions. These vegetation changes influence habitat availability for wildlife, water filtration efficiency, and ground stability. Human navigation difficulty may change accordingly as plant density and composition shift. Wildlife distribution responds to climate factors too. Species adapted to specific temperature or water conditions may relocate. New predator-prey relationships sometimes emerge. Disease vectors such as mosquitoes may expand into regions previously unsuitable for them. Public health monitoring increasingly considers wetland-climate interactions. Water chemistry evolves with changing climate patterns. Increased runoff from extreme rainfall can introduce additional nutrients or pollutants into wetlands. Altered salinity levels affect aquatic organisms. Temperature shifts influence dissolved oxygen levels. These chemical changes cascade through ecosystems, affecting biodiversity and water quality. Human settlement patterns often adjust slowly compared with environmental change. Communities established near wetlands decades ago may face new flood frequencies or water level fluctuations. Infrastructure designed under past climate assumptions may require modification. Urban planning increasingly incorporates climate-adaptive wetland management. Agricultural practices intersect with wetland climate dynamics. Changing precipitation patterns affect irrigation needs. Nutrient runoff influences wetland health. Conservation buffer zones around wetlands help mitigate agricultural impact while maintaining ecosystem services. Technological monitoring provides valuable insight into wetland climate trends. Satellite observations track water extent changes. Remote sensors measure temperature, salinity, and vegetation health. Data integration supports predictive modelling, helping anticipate future conditions. Scientific research continues examining feedback relationships between wetlands and climate. Wetlands store carbon, yet can release methane. The balance depends on water levels, temperature, and vegetation. Understanding these dynamics informs climate mitigation strategies. Public policy increasingly recognizes wetlands in climate adaptation planning. Preserving natural floodplains reduces infrastructure damage. Restoring degraded wetlands enhances carbon storage. Integrating ecological knowledge into policy supports resilience. Community education plays a crucial role. Awareness of changing wetland conditions helps residents prepare for evolving risks. Local observation often detects subtle changes before large-scale data analysis confirms them. Economic implications follow ecological shifts. Fisheries productivity may change with water temperature and salinity. Tourism patterns adjust as wildlife distribution shifts. Infrastructure investment decisions consider flood risk projections. Health considerations also evolve. Expanding mosquito habitats influence disease surveillance. Waterborne pathogen patterns may shift with temperature and precipitation changes. Public health systems adapt accordingly. Cultural relationships with wetlands adjust over time. Traditional practices sometimes require modification when environmental conditions change. Cultural resilience often involves blending historical knowledge with new scientific information. Engineering responses to climate-driven wetland changes include levee adjustments, managed retreat strategies, and restoration projects. These interventions aim to balance human safety with ecological preservation. Insurance and risk assessment industries increasingly incorporate wetland climate data. Floodplain mapping updates reflect new rainfall patterns and sea level projections. Property planning decisions depend on these assessments. Environmental ethics discussions emphasize intergenerational responsibility. Preserving wetlands supports future ecological stability. Climate-driven wetland loss raises questions about sustainable development. Education programs integrate climate science into wetland interpretation. Visitors learn not only about current ecosystems but also about projected changes. This knowledge fosters informed public engagement. Urban green infrastructure often includes constructed wetlands designed with climate resilience in mind. These systems manage stormwater while supporting biodiversity. International cooperation addresses transboundary wetland systems affected by climate change. Shared river basins require coordinated management across political boundaries. Indigenous knowledge contributes valuable perspective. Long-term observation traditions sometimes detect environmental shifts before formal scientific documentation. Ultimately, climate change does not introduce entirely new risks to wetlands, but amplifies existing dynamics. Water levels fluctuate more dramatically, vegetation shifts faster, wildlife patterns change, human interaction requires ongoing adaptation, and as environmental change reshapes wetlands, scientific exploration becomes increasingly important, both to understand evolving ecosystems and to develop safe methods for studying them, which naturally leads toward considering how modern research teams investigate swamp environments while balancing safety, conservation, and scientific discovery. Exploring swamps today looks very different from what it did even a century ago. Early explorers relied heavily on local guides, basic navigation tools, and trial and error experience. Modern scientific study, by contrast, combines field observation with advanced technology, interdisciplinary collaboration, and carefully designed safety protocols. The goal is not simply to traverse wetlands, but to understand how these ecosystems function, how they change over time, and how human interaction can remain sustainable while minimizing risk. One of the biggest changes involves remote sensing technology. Satellites now monitor wetland extent, vegetation health, and water levels continuously. Multispectral imaging reveals information invisible to the naked eye, such as plant stress, nutrient levels, or sediment patterns. Scientists can observe seasonal flooding cycles, track shoreline changes, and detect early signs of ecosystem disruption without constant physical presence. This reduces both environmental disturbance and human exposure to difficult terrain. Drones have added another layer of observation. Lightweight aerial drones allow close-range mapping of areas that would otherwise require difficult ground access. Researchers use them to survey wildlife populations, measure canopy density, assess erosion, and monitor restoration projects. Drone data also supports emergency planning by identifying safe access routes and hazardous zones before field teams enter. Ground-based study remains essential despite technological advances. Field researchers collect soil samples, water quality data, plant specimens, and wildlife observations directly. These activities require preparation tailored to swamp conditions. Waterproof equipment, breathable protective clothing, insect protection, and navigation redundancy form part of standard protocols. Teams rarely work alone. Communication plans, emergency check-in schedules, and clearly defined routes help maintain safety. Water quality monitoring represents a core component of swamp research. Scientists measure parameters such as pH, dissolved oxygen, nutrient concentration, microbial presence, and pollutant levels. These data help assess ecosystem health, inform conservation policy, and detect environmental threats. Portable testing kits allow on-site analysis, while laboratory studies provide deeper insight. Biodiversity research in wetlands covers multiple scales. Botanists study plant communities and succession patterns. Zoologists monitor fish, amphibians, birds, mammals, and insects. Microbiologists investigate bacterial and fungal communities. Environmental DNA sampling has become particularly valuable. By analysing genetic traces left in water or soil, researchers can detect species presence without direct observation. Climate research increasingly focuses on wetlands because of their carbon storage capacity. Peat core sampling reveals historical climate records through preserved pollen, charcoal particles, and chemical signatures. These natural archives extend environmental history back thousands of years, helping scientists understand long-term climate cycles. Hydrological studies examine water flow patterns, sediment transport, and flood dynamics. Sensors placed strategically throughout wetlands measure water levels continuously. Combined with rainfall data and remote sensing imagery, these measurements support predictive modelling of flood risk and ecosystem response. Restoration ecology has become an important research area as well. Many wetlands were drained or altered historically. Modern projects aim to re-establish natural hydrology, vegetation, and wildlife populations. Scientists monitor restoration success through vegetation surveys, water chemistry analysis, and wildlife tracking. Wildlife tracking technology has improved dramatically. GPS collars, acoustic transmitters, and motion-sensitive cameras allow researchers to monitor animal movement patterns with minimal disturbance. These data inform conservation strategies, disease surveillance, and habitat management. Public health research intersects with swamp study too. Monitoring mosquito populations, pathogen presence, and waterborne disease risk informs health policy. Collaboration between ecologists and epidemiologists helps predict outbreak conditions. Educational outreach accompanies scientific research increasingly. Universities, conservation organisations, and government agencies offer field courses introducing students to wetland ecology. These programs emphasise both scientific method and safety awareness. Citizen science initiatives contribute valuable data. Volunteers participate in bird counts, water sampling, plant surveys, and photographic monitoring. Such involvement increases public understanding while expanding research coverage. Safety technology continues evolving. Waterproof communication devices, satellite messengers, and real-time GPS tracking enhance field team coordination. Personal locator beacons allow rapid emergency response in remote wetlands. Protective equipment design has improved as well. Breathable waterproof fabrics reduce heat stress. Insect-resistant materials improve comfort. Lightweight flotation gear assists in deeper wetland zones. Ethical research practices emphasize minimal environmental impact. Researchers avoid disturbing nesting sites, limit vegetation trampling, and follow wildlife handling guidelines. Institutional review boards often oversee study design to ensure ethical compliance. Data integration across disciplines supports comprehensive understanding. Hydrologists, biologists, climatologists, geographers, and social scientists collaborate increasingly. This interdisciplinary approach reflects wetland complexity. Funding for wetland research has grown, partly due to climate change concerns. Governments and international organisations recognise wetlands' role in carbon storage, flood mitigation, and biodiversity preservation. Indigenous knowledge integration has gained recognition. Local communities often possess detailed ecological understanding developed over generations. Collaborative research respects traditional knowledge while applying modern scientific tools. Policy applications of research findings influence land management. Wetland protection regulations, development restrictions, and conservation incentives often rely on scientific data. Tourism management benefits from research too. Visitor infrastructure placement, educational signage, and safety guidelines derive from ecological understanding. Technological advances in laboratory analysis complement fieldwork. Genetic sequencing, isotope analysis, and advanced microscopy reveal processes invisible during field observation. Long-term monitoring programs provide continuity. Consistent data collection over decades helps detect gradual environmental trends that short-term studies might miss. Communication of research findings has expanded beyond academic journals. Documentaries, public lectures, interactive exhibits, and online platforms share knowledge widely. Climate adaptation strategies increasingly incorporate wetland research. Predictive models inform infrastructure planning, conservation priorities, and emergency preparedness. Economic valuation studies quantify ecosystem services provided by wetlands. These analyses support policy decisions by demonstrating tangible benefits. Ultimately, modern swamp exploration combines respect for environmental complexity with technological capability. Scientific study seeks understanding rather than conquest, balancing curiosity with conservation. And as research continues revealing ecological processes, attention also turns toward the human psychological experience of these environments. Because isolation, sensory conditions, and unfamiliar terrain influence perception and emotional response in ways that affect safety and decision-making, which leads naturally toward examining how swamp environments impact human psychology during extended exposure. Spending time in a swamp environment affects more than just physical comfort or navigation ability. Psychological responses begin shifting almost immediately, sometimes subtly enough that people do not recognize what is happening at first. Wetlands combine humidity, repetitive scenery, limited visibility, constant background noise, and unfamiliar wildlife cues into a sensory environment that differs significantly from urban settings or even typical forests. These factors do not automatically cause fear or distress, but they can influence perception, decision-making, and emotional state in ways worth understanding. One of the most immediate psychological effects involves spatial uncertainty. Humans rely heavily on visual landmarks to maintain orientation. Buildings, hills, road patterns, and distinctive trees help anchor perception. Swamps often lack such clear markers. Vegetation repeats. Water surfaces reflect surroundings. Trails appear temporary or non-existent. This uniformity can produce mild disorientation even when navigation tools are available. The brain prefers stable reference points, and when those disappear, mental effort increases. That increased mental effort contributes to cognitive fatigue. Continuous attention to footing, insects, temperature, and direction consumes working memory resources. Over time, concentration declines. Decision-making may slow or become less precise. This does not imply panic. It simply reflects how sustained environmental monitoring taxes attention systems. Sound plays a strong psychological role too. Swamps rarely become completely quiet. Insects produce steady background noise. Amphibians call rhythmically. Birds vocalize intermittently. Water movement adds subtle sound layers. This constant acoustic presence can feel soothing to some people and unsettling to others. Individual perception varies, but continuous noise reduces opportunities for auditory rest. Lighting conditions influence mood as well. Filtered sunlight through dense canopy reduces brightness compared with open landscapes. Lower light levels can create a subdued atmosphere. While not inherently negative, reduced brightness sometimes contributes to mild tension, especially for people accustomed to well-lit environments. Humidity affects psychological comfort indirectly through physical sensation. Persistent dampness can create a sense of stickiness or heaviness. Clothing rarely feels completely dry. Combined with warmth, this sensation may increase irritability or reduce tolerance for minor inconveniences. Again, awareness helps normalize the experience. Isolation perception deserves attention. Wetlands often appear remote even when located near populated areas. Dense vegetation blocks sightlines. Sound transmission becomes unpredictable. Communication devices may function less reliably. These factors can produce a heightened awareness of being alone, even when others are nearby. Cultural associations influence psychological response too. Media portrayals often depict swamps as mysterious or threatening. Such narratives shape expectations before any actual experience occurs. Someone entering wetlands with dramatic expectations may interpret ordinary environmental cues as more ominous than they are. Fear responses, when they occur, usually relate to uncertainty rather than specific threats. Limited visibility means potential hazards cannot always be seen in advance. The brain sometimes fills information gaps with cautious assumptions. This evolutionary mechanism supports survival, but can feel uncomfortable in unfamiliar environments. Training and experience significantly moderate psychological effects. Field researchers, conservation workers, and local residents often report increased comfort over time. Familiarity reduces cognitive load. Environmental cues become interpretable rather than ambiguous. Group dynamics influence perception as well. Travelling with others often reduces anxiety compared with solitary movement. Shared observation distributes cognitive effort. Conversation also counters feelings of isolation. Time perception sometimes shifts in wetlands. Repetitive scenery, constant sound, and steady movement pace can make time feel slower. Some people find this calming, others experience impatience. Neither reaction is unusual. Sleep quality during extended wetland stays may differ from typical environments. Humidity, insect noise, and unfamiliar surroundings can disrupt rest initially. Adaptation usually occurs after repeated exposure, but short visits may include adjustment periods. Attention allocation becomes critical. Focusing too narrowly on one aspect, such as insect annoyance, may reduce awareness of footing or navigation. Balanced attention supports safety. Psychological resilience techniques help. Maintaining hydration, scheduling rest breaks, and acknowledging environmental discomfort as temporary improve overall experience. Mindful breathing or brief pauses to observe surroundings calmly can reduce tension. Environmental education reduces fear by replacing uncertainty with knowledge. Understanding why insects behave as they do, how plants grow, or how wildlife avoids humans reframes perception. Technology influences psychological comfort. GPS navigation, reliable communication devices, and weather forecasting tools provide reassurance. However, over-reliance without backup planning can introduce risk if devices fail. Historical accounts often mention psychological adaptation. Early explorers described initial unease followed by increasing familiarity. Similar patterns appear in modern fieldwork reports. Cultural traditions sometimes include practices supporting psychological adaptation to wetlands, such as communal storytelling, ritualized preparation, or shared environmental knowledge transmission. Safety training often incorporates psychological awareness. Recognizing early signs of stress, fatigue, or disorientation allows proactive adjustment before problems escalate. Environmental design for wetland tourism considers psychological factors. Boardwalks, observation platforms, and interpretive signage provide structure that reduces uncertainty while preserving natural experience. Conservation messaging sometimes emphasizes positive emotional connection to wetlands. Appreciating biodiversity, bird calls, or plant diversity can counterbalance discomfort. Emergency preparedness includes psychological readiness. Knowing procedures reduces anxiety if unexpected situations arise. Climate change may alter psychological experience too. Increased extreme weather events, changing wildlife patterns, or shifting water levels influence perception of stability. Scientific research into environmental psychology increasingly examines wetland exposure. Studies explore stress response, attention restoration, and emotional perception in natural settings. Interestingly, some research suggests wetlands can promote calm when perceived as safe. Water presence, rhythmic sound patterns, and biodiversity observation sometimes support relaxation. Individual differences remain significant. Personality, prior experience, cultural background, and physical comfort all shape psychological response. Ultimately, psychological effects in swamp environments reflect interaction between sensory conditions, expectations, physical comfort, and knowledge. Awareness transforms uncertainty into manageable experience, and after exploring physical hazards, ecological importance, historical encounters, and psychological response, it becomes natural to reflect on how humans can approach wetlands with respect rather than fear, recognizing both their risks and their value, which leads toward a broader closing perspective on coexistence with these complex ecosystems. Spending time thinking about swamps often changes how people see them. At first, the focus usually lands on difficulty: mud that shifts underfoot, insects that seem relentless, humidity that never quite lifts, vegetation that slows every step, and wildlife that remains mostly hidden, but occasionally reminds you that you are not alone. Those impressions are understandable. Wetlands ask for attention. They reward patience rather than speed. They rarely accommodate careless movement. Yet after looking closely at how they function, another perspective tends to emerge, one that balances caution with appreciation. Swamps operate through quiet processes. Water moves slowly, sometimes almost imperceptibly. Plants grow in layered patterns shaped by saturation rather than dryness. Soil accumulates gradually as organic material decomposes at a slower pace than elsewhere. Microorganisms recycle nutrients continuously beneath the surface. These processes rarely attract dramatic attention, but their cumulative effect shapes entire regions. Flood control, water purification, biodiversity support, and climate regulation all connect back to these subtle mechanisms. Human perception often favours environments that respond quickly. Roads stay firm, buildings remain predictable. Temperature control happens at the push of a button. Swamps follow different timelines. Seasonal rhythms dominate, water levels fluctuate naturally. Vegetation expands or retreats depending on rainfall, temperature, and soil chemistry. Learning to observe these slower rhythms helps reduce frustration and increase understanding. Respecting wetlands does not mean romanticizing them. The physical challenges discussed earlier remain real. Preparation still matters. Appropriate clothing, navigation awareness, insect protection, hydration, and environmental knowledge continue to support safe interaction. Respect simply means acknowledging that these ecosystems function according to their own internal logic, rather than human convenience. Education plays a central role in shaping that perspective. When people learn how wetlands filter water, store carbon, support fisheries, and protect coastlines, the narrative shifts from dangerous wasteland to complex ecological asset. Public awareness campaigns, conservation programs, and environmental education increasingly emphasize this broader view. Scientific research reinforces that understanding. Studies consistently show that intact wetlands reduce flood damage, improve downstream water quality, and support biodiversity that benefits agriculture, fisheries, and climate stability. These findings influence policy decisions, urban planning, and conservation priorities worldwide. Local communities living near wetlands often embody practical respect already. Generations of experience produce knowledge about seasonal patterns, safe travel routes, sustainable resource use, and environmental indicators. Integrating this local expertise with scientific research strengthens conservation outcomes and public safety. Cultural attitudes toward wetlands continue evolving. Literature, film, and media once emphasized mystery or threat almost exclusively. Contemporary storytelling increasingly highlights ecological importance alongside adventure narratives. Balanced representation helps shape public perception. Urban planning has begun incorporating wetlands intentionally rather than treating them as obstacles. Constructed wetlands manage stormwater in cities. Green infrastructure projects preserve natural floodplains. These approaches recognize that working with ecological systems often proves more sustainable than replacing them. Tourism provides another avenue for respectful engagement. Boardwalks, guided tours, observation towers, and educational exhibits allow visitors to experience wetlands safely while minimizing ecological disturbance. Responsible tourism supports conservation funding and public awareness simultaneously. Technological innovation also supports coexistence. Improved water purification methods, protective clothing, navigation tools, and environmental monitoring systems reduce risk while allowing closer study. These tools do not eliminate environmental challenges but help manage them effectively. Climate change adds urgency to wetland respect. Rising sea levels, altered precipitation patterns, and temperature shifts threaten many wetland ecosystems. Protecting existing wetlands and restoring degraded ones contributes to climate resilience. These efforts benefit both natural systems and human communities. Conservation success stories illustrate what is possible. Wetland restoration projects have improved water quality, revived wildlife populations, and reduced flood risk in multiple regions. These outcomes demonstrate that careful management yields tangible benefits. Personal experience often reshapes perception most strongly. Individuals who spend time observing wetlands, listening to bird calls, noticing plant diversity, watching water patterns, frequently report increased appreciation. Familiarity replaces uncertainty. Psychological research suggests natural environments, including wetlands, can support stress reduction when perceived as safe. The steady sounds of insects or water movement sometimes promote relaxation. Interpretation influences emotional response significantly. Ethical considerations increasingly guide wetland interaction. Avoiding litter, respecting wildlife distance, staying on designated paths, and supporting conservation initiatives reflect responsible engagement. Small actions accumulate into broader impact. Economic valuation studies reinforce ecological arguments. Calculating flood prevention costs avoided, fisheries supported, and water treatment savings highlights wetlands' tangible contributions. Policymakers often respond to such measurable benefits. Future generations will likely interact with wetlands differently than past ones. Education, technology, and conservation awareness continue expanding. Maintaining that progress requires sustained effort. Public participation strengthens conservation outcomes. Citizen science projects, volunteer restoration efforts, and educational outreach programs build community investment in wetland health. Scientific uncertainty remains part of the picture. Ecosystems are complex. Climate interactions evolve. Continued research helps refine understanding and guide adaptive management. Ultimately, swamps remind us that environments do not need to be comfortable to be valuable. Difficulty and importance often coexist. The very traits that challenge human movement, persistent water, dense vegetation, rich microbial life, enable ecological functions that support broader environmental stability. Approaching wetlands with respect means recognizing limits without abandoning curiosity. It means preparing carefully, observing patiently, and appreciating complexity without forcing simplification. It also means acknowledging that coexistence requires balance rather than domination, and with that perspective in place, the conversation naturally keeps flowing, because wetlands continue changing, science continues learning, and human understanding keeps expanding alongside the ecosystems themselves.